Welcome to the ARM Microcontroller Masterclass, version 2. In version 1, I stopped at USART initialization. In this version, 4 more projects are added, including receiving a character using USART, transmitting a character to a computer using USART with automatic code generation by CubeMX, and getting a taste of HAL, which is the hardware abstraction layer, receiving from a computer using interrupts, and a KiCad tutorial which I show how to create a circuit based on the application notes from a manufacturer, in this case the FTDI chip that I'm using for the USART communication. This course aligns with university-level classes such as embedded systems, microprocessor architecture, digital systems design, and introduction to electronics programming. It also serves as a prerequisite for advanced subjects like real-time systems, embedded C programming, IoT device design, and hardware-software integration. And it will be updated regularly with enhanced editing of this video for brevity and clarity, and additional projects that have yet to be added. So make sure to subscribe to stay updated on the latest videos, revisions, and new lessons. Now here's what you'll learn in this course. We'll begin with an introduction to bare chip development, learning to work directly with ARM microcontrollers at the register level. Then we'll go through the prototyping setup, software setup, an introduction to STM32Cube IDE, and how to create a project in the IDE. We'll learn transferring the program to the microcontroller and using SCM Studio to monitor and visualize data. Next are real troubleshooting scenarios. Then the 4 most important code instructions, changing and testing bits. After that, we'll begin the projects. Turning on an LED, the Hello World of MCU projects, receiving input from a button, latching an input, interfacing an LCD display, sending integers on the LCD, sending floating point numbers on the LCD, and setting the location on the LCD. We'll then move on to analog to digital conversion with ADC conversions using the internal temperature sensor, converting the ADC value to a meaningful number, temperature, using a potentiometer as the ADC input. Next, we'll tackle timers and counters with prescaler, where it skips oscillations, and auto reload register, count direction, and center aligned mode. Then we'll explore PWM, pulse width modulation. Introduction to PWM signal generation, creating an ADC header file, control PWM operations with the ADC, control the dimming of an LED using PWM and a potentiometer, control a hobby servo with the PWM output, control a hobby servo with a potentiometer connected to the ADC. Then we'll move into interrupts. Introduction to interrupts, using interrupts for ADC conversion, using interrupts for ADC conversion with 2 channels, fixing an artifact on the LCD, push-button interrupt, internal interrupts on 2 pins, switching output to STM Studio rather than the LCD. Then we'll cover communication protocols, introduction to I2C communication, communicating with the ADXL 345 accelerometer using I2C, writing a single byte, communicating with the ADXL 345 accelerometer using I2C, reading a single byte, introduction to USART and other communication protocols, changing the clock speed to 48 MHz because we'll be using that with the USART, transferring using the USART, receiving a character using USART, transmitting a character to a computer using USART with automatic code generation by CubeMX, and getting a taste of HAL, which is the hardware abstraction layer, receiving from a computer using interrupts, and a KiCad tutorial which I show how to create a circuit based on the application notes from a manufacturer, in this case the FTDI chip that I'm using for the USART communication. By the end of this masterclass, you'll have completed over 25 hands-on projects, mastering the STM32 architecture from registers to real-world applications. This is version 1, and new modules and hardware demos are always on the way. All of the chapters and projects in this course can be easily navigated using the timestamps in the description below. This is the most comprehensive instruction on the internet in video form for this subject. If you'd like to delve deeper into more advanced topics like sophisticated PCB design, higher level programming using the HAL or hardware abstraction layer, or CubeMX, check out Phil's lab. I've left a link in the description. This is an STM32 microcontroller. It is an ARM-based chip. So what is a microcontroller? A microcontroller is a device that can receive input, as in ones and zeros, and communication from other devices like a computer or from various devices that provide different types of communication.
It can receive an analog voltage using the onboard analog to digital converter. So it takes an analog voltage, which could be anywhere between 0 and, let's say, 3.3 volts, and convert that into a digital number. The microcontroller can also output. It can create an output in the form of a 0 or a 1. You can control devices using this type of output, like say turning on an LED or turning off an LED, communicating with devices like an LCD, turning on and off various digital lines of an LCD. You can also output a digital like analog signal called a PWM, where it outputs a digital signal that can be between 0 and a voltage reference like 3.3 volts and anywhere in between. One of the coolest things about the microcontroller is that you can sense the environment, and that's part of an input. Specifically, it could be you're sensing temperature, and the temperature would be converted to a voltage, and then you can convert that voltage into a number on the microcontroller specifying the temperature. You can also control much higher power devices. Microcontrollers are everywhere. They're used in almost every electronic device that would be inside of a home or inside of your car. These microcontrollers are used in smart home devices and the Internet of Things, wireless devices, washing machines, TVs, monitors, computers. It controls the efficiency of your engine in your car. It's used in robotics. It can also be tied together to create a much more complex system, used in critical applications where lives are dependent on the functioning of the microcontroller. If you were starting your project from the actual chip itself and building from that chip out using only the components that you need, then you've already built in a more efficient design for the project. When you're developing from the bare chip, you're not bound by any specific chip, as long as you know the fundamentals of programming from the bare chip. There's a wide selection of ARM-based chips out there, and there might be some variations in the data sheet, but that's easy to just reference when you need to. The programming that you have to do to make an Arduino work and the program that you have to do to make a chip function in the same respect as the Arduino is very, very similar. So the microcontroller that I'm holding in my hand right now, it's obviously very difficult to interact with this microcontroller the way it is here. Microcontrollers can be broken out into pins like this, where you just plug this into a breadboard. And breadboards are used for prototyping, where you develop your circuit on the actual breadboard itself, where you have all of your discrete components taking advantage of the pins of this microcontroller. This is an example of how you use the microcontroller. So you have the microcontroller like this that is in the middle of this circuit board here. The circuit board is only the microcontroller, and it's broken out into these pins. That's it. There's no other components on this circuit board, so you know that you're designing specifically for this chip. And then when you go to create your product, all of the components you add around the microcontroller, you can easily design in your PCB designing software when you decide to put out a product. The device that allows you to connect the computer to the STM32 microcontroller is the programmer, and it allows you to send the programs that you create to the microcontroller. The programmer also allows you to connect the microcontroller to the STM Studio to monitor the variables that you wish, to graph the variables that you wish, and also to debug the program while it's running. ST also make a programmer like this you can purchase if you're looking for something that is directly from ST Micro. The device provides 3.3 volts of power for the microcontroller to run. It also has a 5-volt power if you need it. And it has two data lines. One is a clock and one is an I/O. These two work together to communicate between the computer and the microcontroller. The power pins of the microcontroller need to be connected to multiple pins on the microcontroller. These two pins here, these two pins over here, and this one pin over here. It can also be connected to a couple pins over here that's used for the analog to digital converter, but you only need to use them when you're using that converter. To be able to power the pins that are around the microcontroller, you need to connect the breadboards all together on the power rails. There are two power rails, one for the plus and one for the minus. And then those pins are connected to those power rails. Pin number 64 is a positive pin. And you'll want the 3.3 volt positive pin from the ST-Link V2 to be plugged into that pin. The ground pin will be connected to pin number 63. Pin number 63 will go to the negative rail, The positive and negative rail will be connected to this next breadboard, negative rail to negative and positive to positive. Pin number 31 will connect to the negative rail, and pin number 32 will be connected to the positive rail. You'll also want to use a 0.1 UF capacitor between pins number 31 and 32, pins number 63 and 64, and pin number 1 is a positive pin, so it needs to be connected to the positive rail, and you'll have a 0.1 UF capacitor between the positive and negative on this rail, so it's as close to this pin as possible. And these two breadboards need to be connected for power as well, so positive goes to positive and negative goes to negative. So when 3.3 volts and ground is connected to these two pins, it will power the rails along the entire length of the power rails on all of the breadboards. The SWCLK, which is the clock, will be connected to this pin here, which is number 49, and number 46 is SWDIO, which is the IO pin. You can see those two pins here, SWCLK and SWDIO. And this diagram here corresponds to the pins in the back of the ST link. You can put a 510 ohm resistor and going to ground on the boot 0 pin, and that boot 0 pin is pin number 60. I'm going to show you how to set up the software environment, the IDE, which is the Integrated Development Environment. This is where you're going to write the programs that's going to be put into the microcontroller to make the microcontroller do something. The IDE also allows you to transfer the program to the microcontroller. I'm also going to add two other programs to this arsenal of programs, and those are the STM Studio and the STM32Cube Monitor. Both of those programs will allow you to monitor what's going on inside the microcontroller in real time. So you can see what's going on, look at your variables, and in the STM32Cube Monitor, you can also control, you can actually make changes to things in the microcontroller. The IDE I'm installing is called the STM32Cube IDE. The IDE is based on the Eclipse IDE and modified to work with the Cube MX by STMicro. Search for STM32Cube IDE and click on the link from st.com. On that page, scroll down below the description and a list of available downloads will be shown. I'm installing the Windows version. You will need to accept the license agreement and either log in or provide your name and email to continue with the download. The download will be in the form of a compressed zip file. Go to the file location and double-click the zip file to open it. I'm going to run the setup application directly from the zip file. The setup wizard will start. I am maintaining all default values for my installation, including the drivers for the ST-Link and J-Link. Now I will add the STM Studio and the STM32Cube Monitor. Both of these programs will allow you to monitor what's going on with the microcontroller. With the STM Studio, it's very simple. You can monitor variables and you can show the variables in some state like a chart, a line chart, a table form, and a bar chart. With the STM32Cube Monitor, you can not only look at variables, but you can also change and control the microcontroller while it's running in real time. So you have much more flexibility with the STM32Cube Monitor than you do with the Studio, but sometimes just going to the Studio and checking a variable really quickly makes a little bit more sense, depending on the scenario. I will install STM Studio first. Search for STM Studio and click on the link from st.com. STM Studio gives you the ability to read and display variables in real time while the microcontroller is running. The download is below the description of the program on the web page. Click the Get Latest link to start the download. You may need to either log in or provide some information, including accepting the license agreement. Open the compressed zip file that was downloaded. I am double-clicking directly from the application in the zip file. STM Studio requires the installation of the GRE, Java Runtime Environment. The program links to the Java Development Kit, but I have found that this does not work. To correct for this problem, you'll need to search for the Java Runtime Environment and install that program instead. You can see here that I installed the Java Development Kit, which is where the installation links to when I click the Yes button. And when I restart the installation of the STM Studio, it repeats the instructions to install the Java runtime environment. So here are the instructions on how to install the Java runtime environment instead. Search for the Java runtime environment on the internet. Click on the link under java.com, Java downloads for all operating systems. You will be taken to a rather technical and non-adorned page with the download links. I am using the Windows Online link to install the Java runtime environment. Once the download is completed, click on the download and follow the installation instructions. Once the Java runtime environment is installed, STM Studio should have no problem installing completely. I am restarting the STM Studio installation. I'm also keeping the default values throughout the installation process. The installation creates a desktop shortcut. My shortcut is hidden in the sea of icons on my desktop, so I wasn't able to find it very quickly. So I use the Windows Start button to start the application. This is what STM Studio looks like. It is a relatively simple application. You specify the file associated with the program, that is on the microcontroller, specify the variables, and view the variables in your choice of a bar graph, line chart, or table view. Now let's install another type of monitor called the STM32Cube monitor. Like the STM32Cube IDE is based on the Eclipse IDE platform, the STM32Cube monitor is based on the Node-RED platform. The STM32Cube monitor allows you to view variables, but the application also allows you far more control over the microcontroller. You can create your own dashboard to control various aspects of the microcontroller while it's running. I will install the Windows option. Follow the same process as with the other applications. It looks like I downloaded the application twice. I think it is letting you download without logging in or providing the name and email information. After the download is completed, you will need to extract the files, so the installation process uses uncompressed files. I just created a temporary folder on my desktop and extracted, or clicked and dragged, the files into this new folder. From that folder, I can double-click the setup application. As with the other installations, I'm keeping the default values. When the installation finishes, it will launch the program automatically. If you are running this under Windows, some of the features of the STM monitor will need access through the firewall. If you are okay with this, click on the Allow Access for either public or private networks. This is what the program looks like when it starts up. You can start the IDE by clicking on the icon labeled IDE. If you have a special place where you want to hold your files and your projects, change the workspace location. I'm keeping it as the default. This message will only appear if you have a previous installation of the STM32Cube IDE. If you have another instance of the IDE, go ahead and click Yes if you want to associate your project files. When you first open the IDE, you'll be presented the Information Center. In most cases, you won't be using the screen, but let's go ahead and click on the Start STM32 project from here. You'll need to select the chip that you're going to be working with. There are so many selections that you will need to use a filter to reduce the number of selections so you can find the chip. The one I'm using is at the top, so it's pretty easy to find, but you can filter using the ARM core type, the series of the chip, like F0, F1, L1, the ST micro product line, the package of the chip, like how many pins that the chip has and the size of the chip. For instance, we are using the LQFP64. The filter labeled Other allows you to filter by specific attributes of the chip. And finally, you can filter by the feature or peripherals that the chip contains. Say, for instance, you wanted the chip to have USB functionality. This is where you would go to find the chip that you need. Now that I know where my chip is, I can go ahead and click on it and press Next. The IDE will start the project creation wizard. You'll need to put in a project name. I'm naming this project Test, Studio, and Monitor since that's what I'm going to be doing. The target language will be C. I want this to be an executable, not a static library, and it'll use the STM32Cube rather than an empty type. Click on Next, and on this page, you can leave everything as default. The code generator options might be something you will change in the future, but in this case, I'm leaving it default. Once you click the Finish button, the project will be created, but it'll also ask you if you want to open the perspective view, and I always click Yes for this. This is the screen you'll be presented when the project is created. This is the .ioc file that is shown that has the microcontroller and the pins in an interactive graphical representation. If you want the initialization code to be auto-generated, this is where you do it. The initialization code is generally just setting up pins and timers and other features of the chip. In the Project Explorer, I'm going to open up the source folder and double-click on main.c. Let's go ahead and click on the Start STM32 project from here. You'll need to select the chip that you're going to be working with. There are so many selections that you will need to use a filter to reduce the number of selections so you can find the chip. The one I'm using is at the top, so it's pretty easy to find, but you can filter using the ARM core type, the series of the chip, like F0, F1, L1, the ST micro product line, the package of the chip, like how many pins that the chip has, and the size of the chip. For instance, we are using the LQFP64. The filter labeled Other allows you to filter by specific attributes of the chip. And finally, you can filter by the feature or peripherals that the chip contains. Say, for instance, you wanted the chip to have USB functionality. This is where you would go to find the chip that you need. Now that I know where my chip is, I can go ahead and click on it and press Next. The IDE will start the project creation wizard. You'll need to put in a project name. I'm naming this project Test, Studio, and Monitor since that's what I'm going to be doing. The target language will be C. I want this to be an executable, not a static library, and it'll use the STM32 cube rather than an empty type. Click on Next, and on this page, you can leave everything as default. Once you click the Finish button, the project will be created, but it'll also ask you if you want to open the perspective view, and I always click yes for this. This is the screen you'll be presented when the project is created. This is the .ioc file that is shown that has the microcontroller and the pins in an interactive graphical representation. If you want the initialization code to be auto-generated, this is where you do it. The initialization code is generally just setting up pins and timers and other features of the chip. In the Project Explorer, I'm going to open up the source folder and double-click on main.c. This is the main entry point of the program and where you'll do most of your programming. The IDE adds a lot of comment lines, so I'm going to remove those, since in these tutorials, I'm going to show you where much of the coding will need to happen. The removal of these comments isn't absolutely necessary. I am removing anything with a /, asterisk, message, asterisk, and a /. So if you want to do this, go ahead and just remove any of those types of lines that you see. The purpose of this program is only to introduce a variable so I can monitor that using the STM Studio or the STM32 Cube monitor. Let's add a variable called test seconds. This variable will need to be a volatile variable. The volatile keyword is added just so the compiler doesn't optimize this variable out. And I'm initializing it as 0 so the compiler can infer that this is an integer. The test seconds variable will be updated in the while loop, which is the never-ending loop. But I don't want it to be updating that quickly, so I'm using a delay that is available from the HAL library. You may have noticed the list that appeared below the HAL delay while I was typing. I used the Control spacebar to get that list, so it'll be a little easier for you to find the functions and variables available to you. This delay is in milliseconds, so I'm using 1000 milliseconds to equal 1 second, and I'm going to increment test seconds by 1 for each iteration of the while loop. Now we are ready to run the project, which is transferring the program to this microcontroller and monitoring the variable we just created. To do this, we need to plug the computer to the programmer, and you'll hear the notification on the computer that something has been plugged in. If this is the first time you're plugging it in, it'll take a little time to install, so just follow the prompts you have with Windows to make sure it's installed correctly. When you are running the program, or transferring the program, or some kind of communication is happening with the SD link and the computer, there will be a red and blue LED that blinks back and forth. And there is also an error condition. I think the error condition is both blue and red are on at the same time. So let's go ahead and transfer the program to the microcontroller.
Use the play button to initiate the transfer of the program and execute the program on the microcontroller. When you do this for the first time, the run configurations will appear. You can also see the run configurations dialog if you press the down arrow next to the play button and select Run Configurations. In this configuration dialog box, click on the Debugger tab. You want to make sure that under the interface section, SWD is selected. The ST-Link serial number does not need to be populated. If you want it to, just press the scan button. I set the reset behavior to none. You may need to set it as under reset. If you are having problems connecting to the target in this case is the microcontroller, then make sure that the connections to the microcontroller are correct and that they're solid. You'll have messages like cannot erase memory or cannot connect to target. Those are all signs of a bad connection from the microcontroller to the ST-Link V2 programmer. After pressing the Run button from the dialog box or pressing the Play button, all of the information that gives you the status of the ST-Link and errors in your program will be in the console tab on the bottom of the IDE. You can see here that I received a target comms error, and that's because I didn't have the USB cable plugged into the ST-Link programmer. In this case, it said error, failed to erase memory. This was because my SWDIO was not connected securely to pin number 46. Sometimes you'll get an error that has to do with the GDB server. This is due to having multiple errors happen when trying to connect to the target. What you need to do is unplug the ST-Link and plug it back in, and then do the run again. I created these errors intentionally so you can understand what action to take. This is what the console will look like once you've successfully programmed the microcontroller. The status will have file downloaded complete, verifying, and download verified successfully, shutting down, and exit. Now let's start STM Studio so we can monitor the variable that we have in the microcontroller. Make sure the ST-Link programmer is still plugged in. We'll use the top pane of the display variable setting. Click the right mouse button and click on Import. We will need to locate the ELF file for the project that we just created. An easy way to do this is to go into the binaries folder of the project that we have in the IDE. Right-click on the ELF file under the binaries and click on Properties. Under Properties, you'll see the location. Just select the entire location, including the ELF file, and copy to the clipboard. You can cancel that to get out of that and go back into the STM Studio. The ELF file contains all of the information about the program, including information about the variables. In the STM Studio Import Variables from Executable dialog box, click on the ellipsis button and paste the clipboard into the file location text box. Don't worry about the unknown symbols error message that pops up if you get one. A list of variables will be shown in this dialog box, and you'll select the test seconds variable. Clicking the import button will add it to the STM Studio. We want to send this variable information to the var viewer 1, which is the chart to the right. Press the play button at the top to start monitoring the variable. You can see that the test seconds count got up to 100 or around 100. That's how many seconds it took me to import the variable into the STM Studio. You can zoom in and out of this chart using the mouse wheel. In the display section of the STM Studio, you can select how you want to see the variable as a chart, a bar graph, or as a table. What would happen if we went back to the program and removed the HAL delay of 1 second? Since this number can get quite large, I made it an integer data type. I'm going to rerun the program, make sure that the ST-Link was able to transfer the program successfully, and go back to the STM Studio and play again. In this case, I had to zoom out quite a bit using the mouse wheel, and you can see how fast the variable is climbing. Now let's try the same thing in the STM32Cube monitor. Start the STM32Cube monitor by double-clicking on the icon labeled MON. You will need to allow access as before, and you'll be presented with the node-RED flow diagram. This is the request, and this is the response. The probe is the ST-Link, so we need to
create that or add that. Click on one of the probe nodes and click on the pencil icon on the probe config line. Click the drop down in the probe name to select the ST-Link. We're going to go ahead and add. Done. You can see that the little triangle, the red triangle, has disappeared. So we're going to go ahead and do the same thing with this. We're going to select the same probe, add, and done. Okay, so those are good. What this is doing is it's creating a dashboard. These are buttons. You can see by this little finger icon. This is where we're going to create the variables. We have our test seconds as a variable, so we can use that. And then it's going to send that to the probe or the ST-Link. And from the ST-Link, once it's passed its request, it's going to create a response. So this is, some people call this a transmit and a receive. So on the receiving side or the response side from the probe, it's going to go back into my variables, which we have to create, and it's going to go to the chart. And we can also use, this is another button, we can clear the graph. All right, so let's go ahead and put the variables in there. So we have to put in our executable. Let's try that first. So let's go ahead and get the executable, the binary. I'm going to go to the properties and select this path here. I'm going to use Control-C to copy it and Control-V, paste it. Let's see, actually, let's put the folder portion of it in the folder area. There we go. Oh, this is a name. Okay, we can name this something else. Just call it the Studio and Monitor. Let's go ahead and click on the test seconds and let's add it, and we're done. So this should be connected with this. So if I double click this, it should be the same. Just go ahead and done. Click on the deploy button to accept the changes and click on dashboard. You can see that our variable is climbing very quickly as expected. If you've gotten this far and you are still with me, congratulations. You are ready to start your journey in ARM microcontroller development. You've actually bricked the microcontroller where maybe you've had an error in the program or you've actually caused the program to do something unintended to the microcontroller. You may have bricked it. Pull the boot 0, which is pin 60, high, and you can use a 10K resistor to do this. And all you're going to do is pull it high using the 10K going to the positive rail. While the pin is pulled high, you would do a full chip erase or full memory erase. You'd use a program called the STM32 ST-Link utility. You can find the ST-Link utility just by searching for it, and it should be the first link, and do the download and installation. It's very straightforward. You can also use this program to program the microcontroller by just loading the file, opening the file, and selecting it from the debug and the binary file. So just double click that and you'll have the file loaded up in this program. It'll also show you the device memory when you have it connected. You can click on the connect to target and you'll see that it'll show you what's on the actual microcontroller at all the memory addresses. And you need to click on this icon to program it. The settings can be changed using this icon, and you can see that it has the firmware version. It has the target information, which is the actual microcontroller, and the mode should be in normal SWD, which is the SWCLK and SWDIO pins that are being used with this ST-Link. And I have mine set at 1.8 megahertz. And to do a full chip erase, you can use this icon here. Since those pins have been programmed as a function of digital output rather than the SWDIO and SWCLK for programming, there's no way for the STM32 ST-Link utility to actually connect to the chip to communicate with it. The only thing you're going to be able to do is get voltage to the circuit, but no communication can happen. So if you try to connect to the microcontroller, you'll see that you're going to get a message like this: cannot connect to target. If you're trying to connect to an STM32 device, please select normal or hot plug mode from target settings menu. And generally these recommendations are not going to help you. First, we need to find the reset pin. And on this development board, the reset pin is located on pin 7. So find pin number 7. We're going to put one end of the resistor on that pin. And I'm using a 500 ohm resistor. And then we're going to pull it down to ground, which will put the chip into reset mode. And then we're going to go to the link utility and we're going to click on the full chip erase, which is a little dynamite button here. And you'll notice that it doesn't do anything. It just locks up. We're going to remove the resistor and you'll see that the full chip erase is in progress. And it erases it successfully. So if I click on the connect to target, you'll notice that it connects perfectly fine. And we can go ahead and program it again, and you'll see that it programs successfully.
Let me show you how I bricked my microcontroller so it doesn't happen to you. You're going to make programs, you're going to program microcontrollers, and you're going to have problems inevitably. So as long as you're not making mistakes like putting the wrong connectors to the microcontroller to permanently fry the microcontroller, you're most likely going to be able to resolve the situation. In making the video that I was intending to upload, changing the microcontroller's clock speed from 8 megahertz to 48 megahertz, every time I write the code in either the auto-generated code to do it or doing it through manual register manipulation, I brick the chip every single time. And it is only when I use the PLL clock. So I'll show you what happens when I do try to transfer this to the microcontroller. Doing it successfully. So it downloaded and verified successfully, but the target is not responding now because I've bricked it. I've put the microcontroller in a state that is broken. I cannot connect to the microcontroller. If I try to download again, you can see that it's in a state that I can download. So it's red, which is a state that it's connected. At least the ST-Link is working. So if I try to do it again, it's going to give me an error. And you can see it says target no device found. And you'll see it says failed to start GDB server. Error in initializing ST-Link device, but it's still red, so it says it's still in a ready state. So you need to fix the microcontroller first before you continue using it. And the way to do that is you have to do a full chip erase. So let me show you how to do that. And this full chip erase will solve 99% of the problems you'll have. You're going to use the STM32 ST-Link utility to do this. So I'm going to double click that. And there's a little dynamite icon. It says full chip erase. So that's what you want to use. And I'm going to be using a resistor connected to pin number 7. Pin number 7 is the reset pin for the STM32 microcontroller, at least this particular one. So you might want to look at the data sheet or the reference manual to see which pin for yours is reset. So I'm going to insert it into pin number 7 here. And then the other leg, the other side of the resistor, is going to go to ground. So the reason why I'm putting a resistor from 7 to ground is because I don't like to bring any pin to the full of 3.3 or the ground directly. I like to put it through a resistor. And this isn't from my own experience of having prior failures. This is from just responses from comments in YouTube. I just try not to do anything that's going to harm a microcontroller. So I want to try to keep it as safe as possible. So I'm going to go ahead and click on the full chip erase, but you have to be kind of quick with this. So have your finger ready. When I press the full chip erase, it's going to just pause for a moment and wait for you to take that out. So I took it out and you can see that it's going through a full chip erase. And now you can see the contents of the memory of the microcontroller. You'll also notice that the red LED is blinking, and that means that it's in a connected state. Before you do any further programming the microcontroller, you want to disconnect from target. So it's disconnected. I can minimize that now and I can go back. And if I want to, I can do another programming of my microcontroller. Because the PLL clock uses the VSSA and VDDA to power its clock, pins number 12 and 13 need to be connected to the power as well. Pin number 12 is connected to the negative, and pin number 13 is connected to the positive. I'm going to go ahead and press OK, and hopefully everything goes well. Okay, we didn't have any errors after the download verified successfully. I wasn't using the VDDA and the VSSA. Let's go ahead and take a look at those, the power domain, and show you why that didn't work. So this is the data sheet for the microcontroller that I'm using. We're going to go to the power supply scheme, the VDDA and the VSSA, which is the same, it's just positive and negative. The PLL uses that portion of the power. I didn't have those two connected, so I would immediately get an error here, and I would have to erase the microcontroller to be able to reprogram the microcontroller. I'm going to show you the lines of code that you'll be using the most. The way to control features and enable features and set features of the microcontroller is to control bits or turn on and off bits in registers. Bits are ones and zeros, and the microcontroller is made up of a bunch of registers, which is like a huge set of control panels with a bunch of switches. Each switch is like a bit. It's either on or off, a 1 or a 0. On is 1, off is 0. And the register has 32 of these bits. You will need to know how to turn on a bit or turn off a bit.
or setting a 1 as a bit, or setting the bit as a 0. You can also toggle a bit inside of a register. So if the bit is a 0, you can turn it into a 1. If the bit is a 1, you can turn it into a 0. You will also need to know how to determine what a bit is in a particular register. So, for instance, when you enable something, you need to wait until a flag or another bit is set before you move on in the program. So I'm going to show you how to write a line of code that will test whether a bit is 0 or 1 and wait until that happens. The example that I'm going to use in this project is to turn an LED on or off. There are multiple registers we have to affect and bits to set in these registers to be able to turn an LED on and turn an LED off. To turn on a bit in a register, or to set a bit as 1 in a register that has 32 bits in length, we need to specify the register. We're going to use the OR operation, which is the pipe character. It's just a vertical character, and equals, and the bit that we're going to be setting, making a 1. To set a bit to 0 or false or resetting a bit, they're all the same. You're going to use what is called the AND NOT operation. So you're going to specify the register, you're going to specify the AND sign or the ampersand sign, equals, and then a NOT symbol, which is a tilde, and then the bit. Toggling a bit, you're going to be specifying the register and the caret character, equals, and then the bit. If we're waiting for a particular bit to become a 1 or a 0, you're going to use a line of code that it starts with while, which is while a condition is true, keep looping until that condition is false, and then it'll get out of that loop. And the condition within this while loop is the register and the AND sign and the bit, and whether that is equal to 0 or 1, or whether that is not equal to 0 or 1, however you want to represent that condition. A scenario where you would use this testing whether a bit is on or off is when you enable something inside the microcontroller, let's say the analog to digital converter. You will have to enable certain aspects of that converter. And once you set something to be enabled, the microcontroller needs some time to be able to make sure that that particular feature is enabled. And the way to do this is to wait using a while statement, a while, a condition, and for a particular flag in that feature to be set. So you try to enable something, and then the microcontroller will set a particular bit to true or false, 1 or 0, when that particular feature is enabled. And then you can move on to the next part of the program. To see an example of the way I'm using the while to wait for something to be set or reset, here I am starting the ADC calibration, which is setting the AD cal in the CR register of the ADC1 control register. And down here, I'm using the while. There is a while this same bit, the AD cal bit, is not equal to 0. If this condition is true, then keep waiting, because it's waiting for this to be a 0. Because we set it to 1, and it's calibrating, and it's waiting to make sure the calibration is completed. And when it becomes a 0 again, it's finished. I could have also said while it's equal to 1. This would have been the same thing. So while I set it to 1, while it's still set at 1, it will keep going through this while loop. And if it becomes 0, then it goes on to the next one. This example is on page 233 of the book. It's not really important at this particular time to understand why or how this is working, because understanding a combination like and not is not the most intuitive thing. So just remember these lines of code to turn a bit on, setting a bit to 1, turning a bit off, setting a bit to 0, or toggling a bit. If a bit is 1, it can become a 0. If a bit is 0, it'll become a 1. With these 4 variations of code, you will be able to affect any register in the R microcontroller, any bit in any register in the microcontroller, and you'll also be able to test whether a particular bit is on or off, 1 or 0, or true or false. Let's put these operations into practice. So I'm going to take an LED and connect it to pin number 37, which is right here. The LED needs a resistor to reduce its voltage, because if we don't put a resistor on here, it's going to burn the LED out. So I'm going to use a 330 ohm resistor. I probably don't need something this large because this is already at 3.3 volts, but a 330 ohm resistor will just make the LED a little bit more dim than its brightest. If you want to figure out the actual resistor you need to use, you can figure that out using this formula. The resistance is equal to the supply voltage minus the LED voltage, which you'll need to know, divided by the current. I lost sound at this point, but if you use 0.01 amps for your current, which is a conservative number, the supply voltage is 3.3, and I use 2 volts for the LED voltage. You'll have to look at the data sheet for your LED if you are using a different LED. And my resistance value came out to be 130 ohms. Let's draw the schematic. You're going to put the resistor in line with the LED. So let's draw the resistor. So this is what the resistor would look like. And now let's draw the LED symbol. And the LED will be connected to the ground power rail. Let's add the resistor and the LED to the breadboard. Make sure to have the LED oriented so the flat side of the LED is connected to the ground rail. Okay, I fixed the circuit so it's a little bit less ugly, and it probably serves better and doesn't act as antennas. Breadboards themselves actually cause a lot of interference in general, and you don't want to create more interference by putting components in with bare wires all over the place. Okay, let's start the IDE. All right, I have a couple programs here open. Let me close those, and I'm going to start a new STM32 project. I'm using the F030R8. I'm going to click Next, and the project name will be LED on-off toggle, and press Finish. We're going to be using this pin here. Exit that, and this is the project that we're using. I'm going to open up core, source, and the main.c is the one we're going to be using. These comments always cloud me, so I'm going to go ahead and take them out. Or I got a comment that I should keep these in, and I probably will for future videos, but I'm taking this out so I'm able to show the program in a very simple state. So this is the entire program. It has an hash include, a prototype for this function here, which is the system clock config. It's configuring the system clock to run at its default 8 megahertz. You can see that the PLL is none. If it was going to be a different speed, it would have a different value here. Like PLL is a multiplier of the system clock. All right, so we don't want to go into the while loop yet. We're just going to be setting up some of the registers to enable the port C pin 6, which is pin number 37, as output. You can use the reference manual to find the registers that you need to change to make something work. So we want the port C pin 6 to be output, but how do we do that? Well, you could read the entire manual, and it is long. It is, see, 767 pages. I've pretty much gone through the entire manual, so you don't have to. So let's see, what do we need to do first? We need to go to the Advanced High Performance Bus Clock Enable Register. So let's look for that. And to do that, I'm just going to use Control F to find, and I'm going to type in Advanced High Performance Bus, ENR. And I'm going to go to the, to the first one. I'm going to just scroll up here, and I should go to the table of contents, and it's not showing up for me. So I'll just press the up to go to the first one. Okay, here we go. And I'm just going to click on this. It's on page 112. And this register allows you to enable the I/O for any of the ports. So we're concerned with port C here.
So we need to enable bit number 19. So let's go ahead and do that using one of our 4 bitwise operations. So we need the AHBENR register, and it's under the RCC, reset, clock, and control. So the way we write that is RCC for the reset, clock, and control. And we're going to use a hyphen greater than symbol to point to, it's like you can think of this as like a little arrow pointing to the particular register that we need. So the one we're going to be looking for is the AHBENR, which is the first option. If you don't see this list, you can click on the control spacebar to get this list. So I'm going to go ahead and click on that, or double click it, space, and I'm going to use the OR bitwise operation to set that bit, and then the equals. And we have to repeat the register name again, but if we press control space, we might be able to find it in here, but that would take too long to find it. So let's go ahead and just start typing RCC, and you'll start to see different things pop up. Underscore AHBENR. I'm going to do the control space again. So now you can see some more options appear. So what we were looking for is the GPIO enable for the C port. And this is the one right here. So we're going to press enter and then semicolon to end our code line. So now we've set the GPIO to be enabled. We can go ahead and start setting up the specific pin as an output. And to do that, we have to modify 4 registers. First register is the mode register. The second register is the output type register. Third one is the output speed register. And the fourth one is the pull up, pull down register. By the way, I am using my book to do all of this because I wouldn't remember all of this information. So the mode register is abbreviated by MODER. The output type is O-type. The output speed is O-speed. And the pull up, pull down is, you guessed it, PUPD register. All right, so let's start with the mode register. And looking at the reference manual again, I'm going to use Control F, search for mode, MODER. And this is general purpose IOs for GPIOs. And I'm going to go to the register description here. So this is the mode register. You can also see the other registers here as well, the type register, speed register, and the pull up and pull down register. When you look at a register like this, it's generally going to show you for the port. And if you look at the mode R0 and 1 and 2 and 3, these are the actual pin numbers for that particular port. So the one we're looking for is port C pin 6. So this is the one we want to adjust. Let's go to newbiehack.com and let's take a look at the board and look at number 37, which is over here on this side. You can see it says port C pin 6. So that's the port and pin we're looking for in the reference manual. So on pin 6, there are various states that you can specify. You can put it in input mode. That's where you'd maybe put a push button or read a 0 or a 1 state coming in from a port, from a pin. You have the general purpose output mode, which is what we're going to be using because we want to output a high or a low signal or a 1 or a 0. We have an alternate function mode, and that's where you can use, let's see, the one we're using is here. The alternate function would be the timer. These are all the alternate functions here on this column. And then you have analog mode. So let's go ahead and set the general purpose output mode. We need to set the first digit here as 1 and then the second digit as 0. You can see it says 0 and 1. So 0 goes here and 1 goes here. So in this mode, 1 and 0, 1 would go here and a 0 would go here. So let's go ahead and do that. We are specifically talking about the GPIO-C, so you can just type in GPIO-C right here, pointing to the mode register. And pressing that, we go down to the mode register. Since we're going to set this to a 1, we're going to be using the OR bitwise operation again. Equals and GPIO. We don't use the C here because this is a general definition of just a particular number for what bit we're going to be changing. So underscore and then mode. Actually, we can press the Control Shift or Control Space and take a look at all of them. So we can find the underscore mode let's just go ahead and type in mode. And we have motor 0, 1 for 0. So let's look for 6. So this is the both of the digits. This is the 0 digit and this is the 1 digit. We need to put a 1 in the 0 space. So that's all we have to do is to set this to a 1. We just use the OR bitwise operation to set this to 1. And then we need to set the second digit, the 1 digit, to a 0. Now we have to set this digit to a 0. And you can see it's already a 0. It's set as 0 as default, but we don't want to trust that because we could be in the middle of a larger program that we may have set it to something else. So we want to always make sure to set it to a 0, even though we really don't need to. So let's go ahead and do that. We're going to do the same thing, GPIO-C, mode register, and we're going to use the AND NOT bitwise operation. I usually keep the NOT next to the bit number because we can do multiple bit changes in one line, which we'll do later on in the series. But right now we'll keep it simple. GPIO. I'll use the control space to get my list. And we're going to go to number 6 again. And this is the second digit. So by using the AND and NOT, we're making this bit number a 0. Let's go take a look at the type. And the type register means that it's either in a push-pull state, which is the reset state, or it's an open drain. And this falls into a category of understanding transistors. I'm not going to bore you with that right now, but to keep it simple, we're just going to be using the reset state, which it's already defaulted as that, but we don't want to trust that. So we're going to go ahead and set this to 0. And this is the O type, output type register. And we're going to reset this one or set it to 0 using the AND NOT bitwise operation. And we're going to use the control space again to go to the one we need. And since this is actually showing you only a single bit, let me show you why that's happening. So you can see that even though this is a 32-bit register, you're only using from 0 to 15, which is 16 bits. All of these other ones are reserved. So we're only needing to either put a 0 or a 1 for that particular pin. So that's why it only needs 16 bits. So we only need to affect a single bit. So it only gives you that option when you look at the list. So you have 0 through 15. So we're just going to go to 6. And that's all we have to do. Now for the speed, we're going to do the same thing. GPIO-C. So let's take a look at what we need to do for the speed. That's the next one here. And we have options of low speed, medium speed, and high speed. And this is really mainly to do with how much current you're going to consume in the microcontroller. So I would recommend if you're just doing something like blinking an LED, just keep it at low speed. In this instance, because both of these have a 1 for the medium and high speed, and there's only 3 options, only putting a 0 at the 0 space, the first digit of that particular pin, is all we need to do. So let's go ahead and do that. So we're going to be using the AND NOT operation again. So we're going to look at the 0 place of pin number 6. So we're just making sure that this is a 0. Even though the reset value or the default value is already 0, we just want to make sure to do that. Now the pull up and pull down register, we are using no pull up and pull down on this pin. Pull up and pull down mean that there's an internal resistor you can use if you want it. You can either pull the pin up to positive voltage or you can pull down the pin to ground. We're not going to worry about that. This is more necessary for using the input. This feature eliminates the need to have an external pull up or pull down resistor if you need it. So we'll go ahead and just make sure that there's a 0, 0 here. So both of these positions will be a 0. 0 position and the 1 position. When I pressed the control space, because there was nothing else in the list, it automatically populated by itself. So this is going to be another AND NOT. We're going to be using 2 of these. I'm using the control space again. Let's go down to pin number 6. I'm just going to do a copy and paste of this line. And we're just going to change this to a 1. So now we've made sure that there's the bits 0 and 1 on pin number 6 are 0 because we're using the AND NOT operation. Now we've set the port C pin 6 to be output, and now we can actually send a high or low signal to the LED. I'm going to do this in the while loop. Actually, no, I'm going to do this outside of the while loop for now. I'm just going to do one version. I'm just going to turn it on. We're going to use a register called the bit set reset register. And it should be in the same chapter as these registers. So let's take a look at that. I'm going to keep going down. This is the port bit set and reset register. And you can see that there's a bit set and there's a bit reset. When you put a 1 in the bit set register, it will output a 1 or a high signal to that pin. If you put a 1 in the bit reset register, it outputs a low signal, or it'll turn off the LED. So it's almost as if you're setting this and resetting this, or putting a 0 in here instead. So what this is going to do is just make sure that this bit set is not set, if that makes any sense. So let's go ahead and do that. So let's go ahead and do that using one of our 3 bitwise operations. So GPIO C, the same thing. We're going to look at the bit set and reset register. So we want to put a 1 in the pin number 6 for the bit set. So we're going to use the OR operation equals, and then we're going to use the pin number is going to be GPIO underscore bit set and reset register. Let's take a look, and you can see the BR is bit reset and the BS is the bit set. So let's look for the bit set for number 6, semicolon to end the line. And now we should have an LED that lights up once we run this program. So let's go ahead and do that. Run the program. If you're doing this for the first time, you may get the run configuration. First, let me plug in the programmer that is also plugged into the microcontroller. Okay, this is the programmer. It's plugged into the microcontroller. And all I have to do is plug the programmer into the computer. Okay, I heard the signal on the computer that it's plugged in. Let's go ahead and program it. Clicking the play button, it's building the project. Proceed with launch. Errors exist in the active configuration of project LED on-off toggle. Let's see. Let's go ahead and proceed. Let's see what happens. Oh, I see. What is this? So if we hover over the X, this is undeclared. In my haste to erase all of the comments, I accidentally erased some vital lines of code. Okay, so I need these. So let's go ahead and do it again. Play, and it should redo everything. Looks like there's no errors. That's good. Now it's waiting for the debugger connection, and there we go. After programming, you can see that the LED lights up. Let's turn off the LED. So if you want to turn the LED off, we're going to use the bit reset register, BR. And let's go ahead and use the play button to build the project and program the microcontroller. And you can see that the LED is off. Let's go ahead and blink the LED. We'll use the toggle. But since the toggle is toggling a single bit, that means that we'll need to find a register that I can update a single bit to turn on and off the LED. Let's take a look at what we have here. If we look at the ODR register under the GPIO, we can set or reset from a single bit. So let's use the ODR6. And if we write a 1 here, the LED will turn on. And if we write a 0 here, the LED will turn off. ODR. And I'm going to use the toggle. Let's find ODR number 6. And I want this inside of my while loop. So every time it goes through the while loop, it will toggle it on and then toggle it off, toggle on, toggle off. But it's going to be going way too fast because there's nothing to slow it down. We won't even be able to see the LED turning on and off. So let's add a delay, a 1 second delay. And we're going to use the HAL delay like we used before. There we go. And the delay is in milliseconds. So we can put 1000 here. And for every second, it'll turn off and on. Let's try that. Press the play button. And now we can see that the LED is turning on and off every second. We'll take a look at using the GPIO, the general purpose input-output, and we'll take a look at the input side of things. Using a push button connected to one of the GPIO pins, and then we'll output to an LED. We'll take a push button switch like this. We'll have the microcontroller read the push button switch on one of the GPIO pins, and then we'll output on another pin, completely different port and completely different pin on an LED. When we press the button, the LED will turn on. For the LED output, I'm going to use the same port and pin that we used in the instructional video for LED output, which is port C, pin 6. And that was located
located on pin number 37, which is right around here. As before, we'll use a resistor and an LED, and it will be connected back to ground. When we output a 1 or high to this pin, we will light up the LED because it's connected to ground. For the input, I'm going to connect the push button switch to pin number 27, which is port B, pin 1. The push button schematic is going to look like this. It's going to come from 27, which is the port B, pin 1, and it's going to have a resistor. And the resistor here is just to protect the pin. It's going to be a 330 ohm resistor. And then this will be the switch. And from the pin, we're going to have another resistor, and that's going to be connected to ground. And the ground resistor will be at a high resistance, so we're not going to be using a lot of current when the switch is actually depressed. This will be a 220k ohm resistor. The resistor coming from the pin will be a 330 ohm resistor. And this resistor really is only to be used when this is going to be connected to VCC. So in the pressed state, you're going to have these two connected. So you're going to have a connection between ground and VCC, which will be at 220k ohms, which is high resistance. So very little current is being used when we're pressing the button. But it's also connecting to the pin at a 330 ohm resistance. So we're protecting the pin, but we're still getting the high signal from VCC. When the push button is not being depressed, you'll notice that the pin is going to be directly connected to ground. And what we're doing here is we're pulling this pin down as a natural state. We're doing this instead of actually pulling the pin down internally. We could do that in software where we use the PUPD, pull up, pull down register, and pull this down, but that's only pulling it down to about 40k as specified in the datasheet. And we're pulling it down at 220k, which is a lot more resistance and will draw less current when the push button is pressed. If we didn't have a pull down resistor externally and we didn't have the pull up, pull down resolved internally, when the push button is not pressed, this would be in a floating state. And you'll notice quite unpredictable behavior. Even waving your hand over the circuit could cause unpredictable outcomes. So when you're putting a circuit together that has an input, that is the mode for the particular pin is set as input, you want to make sure that it's either pulled down or pulled up and not in a floating state, because that input is going to be acting like an antenna and can pick up noise. And if that noise goes above or below the thresholds for TTL circuits, transistor to transistor logic circuits, it will produce an outcome, make the LED turn on or do some other unpredictable effect if you have a much more complex circuit. Now that we understand how the circuit works, we can go ahead and put together the circuit on a breadboard. The first thing you'll want to do, if you haven't done so already, is set up your board so you'll have all of your power connected and all the power rails connect together. And this power connected, the power connected from the bottom of the board, and you have the boot 0 connected to ground with the 510 ohm resistor. Let's get started by connecting the LED to port C, pin 6. And that's on the pin number 37. Insert the 330 ohm resistor across the two tie strips, and then the LED with the flat side towards the ground. So from pin 37, we have a 330 ohm resistor to an LED that is connected to ground. Now we can connect the switch to pin number 27, which is port B, pin 1. We'll start with the 330 ohm resistor, connecting the two tie strips. Then we'll put the switch, allowing the lead of the switch in the back here to share one of the spots in the tie strip with the resistor. So it can give me enough room back here to put the other resistor. And we'll put the 220 ohm resistor on that same tie strip to ground. Now we only have to put in the connection from VCC to the other side of the switch. So now when the switch is depressed, this lead will be connected to this lead. And VCC will be connected to ground through a 220k resistor. And it'll also be connected back to pin number 27 with the 330 ohm resistor. We're going to be looking at the GPIO input registers, or the registers we need to use to make the input happen. The registers that we use for the input is very similar to the registers we're going to use for the output. In fact, some of them are the same. We're going to look at the mode register, the O-type register, which is the output type register. We probably won't be using that one. The speed register, the pull-up, pull-down register, and one new one is the IDR register. The switch is going to be connected to the input pin. We need to figure out how to get the information from the input pin. We're going to need to know whether there's a 1 or 0 on that pin. Since we need the microcontroller to act on when the pin is 1, we need to figure out how to do that. And the couple ways to do that is by polling it, meaning we're going to test that pin every time we go through the loop. So every time we go through the loop, we're going to test whether there's a 1 on that pin. The other way is using an interrupt. In the interrupt, the microcontroller will tell us automatically, and it will go into another part of the program called subroutine or a method. In this video, we're going to be using the polling method. So let's get started. Okay, let's create our pseudocode. We need to include the library. Since we have skeleton code, it really doesn't know how to control the chip, the microcontroller. So we need to include that library in there. In the main section, we need to set up the control registers for the LED output. And we need to set up control registers for the input. And in here, when turn on LED, when button is pressed. Okay, so that's a very simplistic pseudocode. We're going to set up the registers. This is where the program enters. This is the entry point of the program. It's going to do some setting up of the output and input. In the loop, we're going to actually test if the button is pressed, and if it is, then we'll turn on the LED. So the button is pressed, turn on the LED. If the button is not pressed, turn off the LED. All right, so in the output, we need to set up the mode register, type register, the speed register, and the pull up, pull down register. And then for the input, we need to set up the mode register for input. Let's go ahead and just put for output up here, and the pull up, pull down. Okay, and the turning on the LED, we've already done that, so we already know that's the BSRR register. And then turning off the LED, we can still use the BSRR, but we can also use the BRR register as well. So when the button is pressed, we're going to use the IDR register. This is the input data register. When we're polling this register, it'll have a 1 if the button is pressed and a 0 if it's not, in that specific bit that we're using. Before we forget, we need to set up the RCC, or the reset and clock control. And within this reset and clock control, the advanced high performance bus. And all we're doing is we're enabling the GPIOs that we need for port C, pin 6, and port B, pin 1. Let's go ahead and take care of the port C, pin 6. We've already done that before, so we'll just go ahead and enter that in. We need to include the library because it doesn't know what we're talking about yet. So let's go ahead and do that. Pound include, and it is the STM32F0XX.H. Reset and clock control, and we'll use the member AHBENR, which is the advanced high performance bus enable register. And we're going to enable the GPIO C. Okay, so we're going to do that same thing to the B, port B. We took care of that. The really cool thing about putting in the pseudocode is because they serve as great commenting and annotations within the program. So you know what it does after you've actually put in the code, and it also helps you put in the code. So let's go ahead and set up the control registers. So we'll do the mode register first. So this is going to be under GPIOC. Under that, we'll have the mode register. So we need the general purpose output mode, which is a 0 and a 1, and we're doing it to the 6th pin. So that'll be a 0 and a 1. So we're going to put in the 1 first. Actually, I did that backwards, didn't I? It'll be, yeah, that's the 1 here, and then that's the 0 spot. So the first spot would be a 0, and the second spot would be a 1. So in the 0 spot, which is this one, we need a 1. In the 1 spot, which is this one, we need a 0. So let's do the 1 first, which is in the 0 spot. All right. And then we need a 0 in the 1 spot. So we're going to use an and a not, as we did in the previous instruction video. So we're ensuring that there's a 0 in the spot. Okay, now the output type. Let's see how that works. In the output type register needs to have it's going to be push-pull in the 6th place. So it's going to be a 0. So we're going to have to use the and not again. Output type 6. Okay, now for the speed, let's see what we need for that one. We're going to have the high speed, so it's a 1 and 1. So that's just going to be 2 ORs, 0, and we're going to OR 1. So speed is taken care of. Now the push-pull, or pull up, pull down register, and we're going to have no pull up, pull down. So we're going to do an and not with a 1, 1. So and equals not GPIO PUPD R. We're going to go to the number 6. And as we learned last time, if this is a 1 in the 0 place, this is a 1 in the 1 place, and this is a 1 in the 0 and 1 place. So we'll use that. And by doing that, we're and notting, making sure there's a 0, 0 there because we're using the not. All right, so let's take care of the input side. So obviously we want the mode to be input. So we want the GPIO B. We're using port B, And then we're going to go to the mode R register, and let's see what that is in the data sheet. So we want input. The input mode is 0, 0. So we can use the mode R1, and we can just use the 1 and 1 using the AND not, just like we did with the pull up, pull down for the output. So we'll use the AND equals not. That should be it. Okay, so now the pull up, pull down is not going to have, it's not going to have any pull up, pull down because we're resolving pulling it down externally. So let's go ahead and do that. Let's see how we do that again. Oh yeah, we're doing it the same way we did this one. So AND equals not. So just to review, we are setting up our mode for output for the LED. We're setting up our output type to be push-pull. We're setting up our speed register for the highest speed. And we're setting up our pull-up, pull-down as no pull-up, pull-down for the output. In the input, we're setting the mode for input, and we're setting no to pull-up, pull-down because we're resolving that externally with that 220K resistor going down to ground. Now in the infinite loop, we're going to be using the polling method. So we're going to say if button is pressed, we need it to do something. And we're going to be turning on the LED. And here we'll use the else. We're turning it off. Now, what do we need to put in the parentheses here? What is the condition? The condition is we're going to be doing some AND bitwise arithmetic. So let's go over how we do this. The IDR register has 16 bits. Each one represents a single pin. If there is a high digital level on one of the pins, then there will be a 1 in one of these bit positions. We have it on 1, port B, pin 1. If we press the button and we put a high signal on that pin, there will be a 1 here. If we have no other switches on these other bits, then all of them will be 0. We need to test whether this is going to be 1 or 0. So let's see how we can do that. We're going to use the AND bitwise operation here. We're going to start with the actual register, which is the GPIO BIDR register. And that register is going to have 16 bits in it. So let's go ahead and put in the zeros. Okay, and then we're going to use a mask, which is the GPIO IDR1 register. And that register, or that number, it's not really a register, this is just a number, it's a mask. Let me divide these into 4s. And because we have a 1 here, it's going to have a 1 in the 1 bit place. This is 0, this is 1. Let me just put the 0 here. 1, 2, 3, and then so on. So in the non-push button depressed state, this will have a 0 in it. But when we depress the button, it will actually have a 1 here. If we use an AND, this is the AND operation, AND bitwise operation. So we're going to do some AND arithmetic here. So 0 and 0 is 0, 1 and 0 is 0, and then 0 and 0 is 0, and so on. So this would be a false statement because 0 generally means false and 1 means true when it comes to if statements. To make this come true, obviously we have to press the button because there'll be a 1 here. So when there's a 1 here, 1 and 1 will equal 1. So that will be a true statement. So by using this mask for this position, which is indicated by this, we can test whether that particular pin and the push button is pressed or not. So let's go see how we do that in code. So we start out with GPIO B IDR. So this is the actual register that will be listening for the pins to be turning into a 1 or a 0, and it's under GPIO B. And the mask, this is an AND arithmetic. The mask is going to be GPIO IDR 1. So this is the mask. This one has a 1 in that location. And you know that 2 in binary is a 0 and a 1. So the first 2 numbers in this is a 4-digit binary number in hex. So this will have a 0 and a 1. This is actually a 32-bit number here, but it only allows us to use half of it. Because in the data sheet, you notice that all of this is not being used at all. It's only the 0 through 15, which is 16 bits, representing each pin on that port. So now we need to turn on the LED. So we'll use the GPIO C and the BSRR register. To turn it on, we're going to use the bit set. So we're going to use the OR bitwise operation, GPIO C. So the bit set register is, so we're turning on the LED. Let me put this comment above. Now we need to turn off the LED if this is a false statement. So GPIO C. Let's go ahead and use the BSRR. We're going to put a 1 in that place for the bit reset. Last time we used the BRR, which is the bit reset register, but we can use the bit set reset register, and you can see it uses all 32 bits, and we'll use the bit reset for number 6. So we're putting a 0 in that pin if this turns out to be false or we're not pressing the button. Of course, in this simple implementation of code for pressing the button, we're not taking advantage of any debouncing or anything like that, because it's just going to turn on when we're pressing it and holding it down. It'll stay on, and it should turn off when we release it. So it's a very simple implementation of using the button. We'll take a look at more complex situations where we're debouncing and when we're using interrupts to turn it on and off. So let's see if this works. Let's see if it compiles. Looks like it compiled successfully, and that was the first time, which is really good. That's where having these come up automatically really helps when you have the library on. It doesn't mean the code will work, but it means that we don't have any syntactical errors. Let's see if this code works. Okay, the microcontroller was programmed. When we press the push button on port B pin 1, you'll see that the LED lights up. We're going to make an LED toggle on and off every time we fully depress a push button and we release a push button. I'm going to add a little bit of complexity to our simple input for push buttons. But because the push button is a mechanical component, we're going to have some problems, because mechanically the signal is going to bounce up and down. So we need to take that garbage out, only consider the pure high or low values on that pin. Push button switches are mechanical components. Within this push button switch, you have leads that have contacts at the leads. Then you have a plate. This is a very simplistic diagram. And when you push down on the push button, this conductive plate creates a contact with the two plates that connect to the leads, creating a complete circuit. This action is going to cause problems electrically because it's mechanical, and mechanical things happen a lot slower than electrical current can. You can have a scenario where a high signal or 1, when you press the button to make a contact ground, it should go low or 0, or vice versa. It could be low, and then when you make contact, it can go to a high signal. That depends on how you have the switch connected. If it's connected to the low when you press it, then it will go low. If you have it connected to the high when you press it, it'll go high. What is actually happening, however, when you're pressing a push button is it's starting low, and then when you press it, it could be doing some jumps before it gets to the high digital level. In software, you're going to be able to see all of this. You're going to see it go from 0 to 1 to 0 to 1 to 0 to 1. And if it goes below the thresholds, then you may see it go back to 0 or not. And then it should, if it's depressed for a period of time, you should see a good signal of high. We would like to eliminate this portion. So when the LED is turning on or is toggling, the LED is going from off to on. So let's say it starts off. We don't want it to turn on until it passes this threshold here. And I'm going to use a counter to count cycles when this is actually constantly on a high or low signal. I'll count it on a low signal and I'll count it on a high signal. So we'll know if it's not being pressed and it's being pressed. And all this stuff will be eliminated in software. If you look at code online, you'll notice that a lot of people will just implement a delay from when it thinks it's pressed, like from here. They'll introduce a delay that they know that if it's still pressed over here, then they know it is an actual pressed. But I don't like that technique because what it does two things. It only tests 2 points to see if it is not bouncing. And it ties up your microcontroller for a specified amount of time, allowing you not to do any other instructions in between that. Alternatively, I would like to have the program on every cycle test either if this is a 1 or a 0. And if it's a 1, every cycle it'll test it again to see if it's another 1. If it's a 0, then it eliminates it. It's not pressed. But when it keeps doing that and it gets to this point, it has to keep doing the cycles until I get maybe 500 or so of these. So I'm able to do other programming within these cycles. I can do all kinds of other code inside of these cycles. With a delay, you'd have to wait from this point to some specified point without doing any instructions or code within the microcontroller. It wouldn't be able to run or execute the code during that time. This is very similar to a state machine where the state machine is cycling through operations and it keeps cycling through and it collects data as it goes and responds to that data. We'll get into state machines in more detail in future tutorials. So specifically, how do we do this? We're measuring a 0 on the pin, and then we'll have some kind of bouncing going on, and then we'll end up on a high level. During this time, we're going to have a few variables we're going to be working with. One variable is going to be, obviously, it's going to be button pressed.
if it's going to be equal to a 0 or a 1, telling me that whether the button is actually pressed or not. And I want to know whether it is actually pressed or not. When it has a good count of high digital level samples, it will be button pressed 1. If it has a good number of samples of a low level, it'll be button pressed 0. So we have to introduce another variable, and we'll call that one button pressed confidence and button released confidence level. And what we'll be doing is we'll be counting up the button pressed confidence level when it matches a high level here, and it'll keep making samples until the number of samples is equal to the threshold that we set for the confidence level. And the same thing with the released. When we're testing it, however, we want to make sure that when we're counting the button pressed confidence level, that's going to be just a counter. We want to count it while the button pressed is 0 because we don't know if it's 1 yet. So while the button pressed is 0, we'll start counting. It could be counting here, but then maybe it doesn't, it shows a 0, so it has to eliminate that confidence level, and the confidence level goes back down to 0. So while the button pressed is equal to 0, and it matches a good number of samples for the button pressed or high level, then we can turn the button pressed variable to 1. And the same goes for the button released confidence level. When it's pressed over here somewhere, and then it starts to do some bouncing, and it finally gets to 0, we want to eliminate all of this bouncing as well. We don't want any of this. So we're going to do the same thing. If it's button pressed as 1, then when it gets through enough samples for when the button is released, then we can say that the button pressed is equal to 0, meaning the button is released. When the button pressed is equal to 1, when we know that the confidence level is high enough beyond our threshold, we will set the button pressed to 1, and then at that particular point, we will toggle the LED. So we'll turn it either on or off. If it was on, then we'll turn it off. If it was off, then we'll turn it back on. So every time you're pressing the button and releasing it, it'll turn on, press it, release it, it'll turn off, press it, release it, it'll turn on, and so on. So we'll have to introduce code to toggle the LED as well. So let's start with a program that we had from the previous video. This is the code where you test whether the pin has a high level digital signal or 1 on it. And we're turning on the LED if it's 1, and we're turning off the LED when it's not 1. So this is just a simple, if you press the button, it turns the LED on. If you release the button, it turns the LED off. In this case, we want to press and release, it turns on, and we want to press and release, and it turns off. So I'm going to eliminate this code right now because we don't really need it yet. We'll be using it in our toggling of the LED. So let's write some pseudocode within this portion here. So when we know that that pin is receiving a 1 on it, we need to measure the confidence of that, or increase the confidence. Once the threshold for the confidence level has been reached, we can toggle the LEDs. When there is a 0 coming in on that pin, we want to increase the button released confidence level. In both of these, we're going to have to include some kind of variable to show us the state of the button pressed once the confidence level has been reached. So we'll call that button pressed. In the released portion, once the button released level, confidence level, we want to update the button pressed variable to 0. We want these variables to lie outside of the while loop because we don't want to keep initializing it while we're in our infinite loop. So we need to do that over here. We only want to do this code when the button pressed variable is equal to 0 because we're trying to make this button pressed variable equal to 1. So it must be 0 when we're doing this portion of the programming. It doesn't make sense to run this part of the code when the button pressed variable is equal to 1 already. It's just a waste of cycles for the processor, and it's not necessary. And it could cause the toggling of the LEDs to happen when you don't want it to happen. So let's go ahead and put in that code. So if the button pressed variable is 0, then do this stuff. Else, we're going to make it so if the is 1, then we can do this code because it doesn't make sense to turn it into a 0, the button press variable to a 0 if it's already 0. So we want to make sure that it's 1 and not run this code unnecessarily. This is all the pseudocode we really need, and it should be self-explanatory. Let's go ahead and start making our real code. We'll start with the variables, and we're going to make them volatile so they're not optimized out when we're doing the building of this code. These variables will remain live and dynamic throughout the running of this code. So we use the volatile, and we'll start with the button pressed variable. So we'll make that a char, relatively small variable, small size variable. It's only 8 bits. A side note with this variable type car is just an integer of 8 bits, and you can have it either signed or unsigned. Signed, if you put signed before it, that means it could be a value from negative 128 to a positive value of 128. But car alone, it's unsigned, is 0 to 255. So we're going to initialize this to be 0. And this is actually really important because if we don't have it 0, then it won't actually get into this portion of the code for it to actually set this to a 1 in the first place. So you want to make sure that it's initialized to 0. So let's initialize our button press confidence level. And it's going to be also volatile. And this one will be an int because it could be a large number. And we'll initialize that to 0. And we'll do the released confidence level. So let's get the low-hanging fruit first. We'll use this variable because we're using it in these if statements. So we can go ahead and just populate that. So let's go ahead and do this. We can increase the button confidence level. And we're going to use the ++, which is the same thing as saying button press confidence level is equal to itself plus 1. So it's adding 1 to this every single time that the pin has a 1 on it. We'll also want to reinitialize the button released confidence because if it's being pressed, then it's obviously not being released. So we can say that's 0. Once the button press confidence is past the confidence level, let's do that. So we're going to have an if statement there. If that is greater than, we don't actually know a real threshold value yet. If it's greater than, let's say 5,000 or 2,000 or 100 or 500, we could introduce another variable. So let's go ahead and do that. And we'll call that confidence threshold. And we'll make that 200 to begin with. Probably way too low, but try that. The faster processors and the more instructions you can run, the greater this threshold needs to be. So you can also use some code to determine the actual speed of the processor and use some divisor or some coefficient to determine this actual number. But let's just go ahead and hard code it for now and see what happens. So that would be confidence. If it's greater than the confidence threshold, then it will do, we don't know what this is going to be yet. Let's go ahead and update the button pressed variable to 1. Now let's work on the bottom part where the button pressed is equal to 1, but the pin is being passed as 0. So we want to increase the button released, and then the button pressed should be 0. And this way, if there was some up and down or bouncing, and it actually got in here, and then it bounced down to 0, then this is where it's actually reinitializing that variable so it doesn't mistakenly think it's being pressed. So let's do this. Once the button level has been achieved, the threshold released confidence level is greater than confidence threshold, then we are going to update the button pressed variable to 0. You'll notice this is constantly increasing whether it is above the threshold or not, but I don't want that to happen. I want, once it's gone above the threshold, like it's reached its 201, I don't want it to be increasing anymore. That may cause some unpredictable behavior because we may be exceeding the level of the int, since this is going to be done in every single cycle of the infinite loop. So let's go ahead and put in an else here. If it's not beyond the confidence threshold, then it does the increment of the confidence levels. And we'll do the same thing to this. Now the only thing we need to do is toggle the LEDs. This is our last set of code statements to put in. So let's go ahead and we're going to need to introduce another variable here because we don't know the state of the LED. We need to store that in some variable. So let's go ahead and put that in. LED lit state, whether it's lit or not. We'll use a car again because it's a small number. It's only 8-bit. We'll call that LED state. And that will be off to begin with. So let's go over here and say if the LED state is equal to 0, then we should turn it on. Else, if the LED state is on, we should turn it off. So let's go ahead and turn the LED state on. It should be equals. Else, if the LED state is on, is 1, we should turn it off. Now we need the code to actually turn on and off the LED. So turn off LED, and over here, turn on LED. Oh, sorry, turn on LED and turn off LED. So when the state is 0, we're going to turn it on. And when the state is 1, we're going to turn it off. So the code to turn on the LED, it's on the C port. So we're going to access the member of the BSRR. We're going to set a 1 in the pin 6 place. The bit set, or the bit, actually no, this is the bit set register. Now we're going to turn off the LED. It's the same, no, it's not the same thing. Access the member of the BSRR again, or the BRR, and we're going to find the BR for bit reset for 6. Okay, the microcontroller was programmed. When we press the button and release, the LED turns on. When we press it again and release, the LED turns off. Let's do this in many successions to see if we get any bounce. So far, so good. So 200 seems to be okay. Let's try decreasing the number and see what happens. Okay, let's decrease our threshold to 20. See what that does. Hit the button a few times. Well, I see the bounce. We will connect an LCD to the ARM microcontroller. LCD communication is no more complex than lighting up LEDs and testing button presses. The only difference to controlling an LCD is the way we turn on and off a pin and the timings between each bit going towards the LCD. The LCD that I'll be using is of the standard flavor. The LCD is powered by 5 volts. It has 16 characters per line and contains 2 lines. The LCD uses the standard 8 data pins, an enable pin, a read-write pin, a register select pin, and the standard contrast input voltage pin. The LCD can be used in either 8-bit mode or can be separated into 2 banks as 4-bit mode, and you'll only need to use 4 wires in 4-bit mode. You might be wondering how we're going to be using a 5-volt LCD with a 3.3-volt microcontroller. The ST link that we use to program the microcontroller contains a 3.3-volt output and a 5-volt output, so we can use that ST link programmer to also supply the voltage for the LCD. In a typical scenario where a microcontroller is communicating to an LCD, you would normally have the microcontroller using a single port, say port C for instance. And port C would have pins from 0 to 7. Those pins would go directly to the data pins of the LCD. And we would simply send a byte to that port because the byte is made up of 8 bits and the port has 8 pins. So the byte would be delivered to the port and each bit would be sent to each pin, each of the 8 pins. An example would be to send the character A, for instance, to the LCD. And the character A has a number, an ASCII code equivalent to 65 in decimal, or 01000001. And the bits that make up the number 65 in binary would be put onto the pins and sent to the LCD. But in the case of this particular microcontroller, we don't have that convenience because we need to find 5-volt tolerant pins. And the 5-volt tolerant pins will not give us a convenient 0 through 7 of a particular port. So we're going to have to send the byte to disparate pins around the microcontroller. So what we need to do first is we need to find out which pins are available to us that are 5-volt tolerant. You might wonder why we actually need to find 5-volt tolerant pins when we're sending characters to the LCD. But while we are sending characters, we also have to determine if the LCD itself is busy. So the only way to do that is to read the pins and determine if we get the busy code or not. This is not actually absolutely necessary because we could just extend the time that we deliver the characters to the LCD, but it's good practice to do this anyway. On page number 27, you'll find the abbreviations for the pins to determine whether it's a 5-volt tolerant pin or not. So you can see here, the FT is a 5-volt tolerant pin. The FT, lowercase f, is a 5-volt tolerant pin, and it is fast mode plus capable, which means that it's capable of turning on and off, sending ones and zeros at 1 megabits per second, which is 1 million bits per second. I'll probably not use this one because I may need that in the future, so I don't want to use those pins. I'm just going to go ahead and get the standard 5-volt tolerant pins. The table of pins actually starts on page number 28 and runs through 32, actually 33, but we're not going to be using this page since it's really only reserved for the ground and digital power supply. Or during this exercise, you're going to really get familiar with the pins on this microcontroller. You'll see that there's a pin number here. There's a column for each form factor of chip. We're using the 64 pin. In this column, this is the actual function, the primary function of these pins, which is generally input-output. The column that's really important to us right now is the I/O structure, which tells you if it is 5-volt tolerant or not. The alternate functions are also very important to us right now because we don't want to be using pins that we'll be using in the future. So we'll be taking a look at that as I mark the drawing to designate
designate which pins are the 5-volt tolerant pins. The alternate functions and additional functions aren't super important at the moment because they actually have quite a number of options that you can use, and a lot of the USARTs and the I2C and the SPI, they're quite varied, and you can use multiple pins for the same function. If you take a function for, let's say, the USART 1 CK, you can use another pin for the same thing, such as here. So don't be too worried about that, and in the prototyping stage, you can always change the pins that you're using. So I'm going to use this table, and I'm going to mark the pins that are 5-volt tolerant on my drawing. The first two pins that are 5-volt tolerant are the PF0 and the PF1, then PF4, 18, and then PF5. The next one is all the way over here at number 28. PB2, the one next to it, PB10, PB11, PB12, which is around the corner here, and then PB13, PB14, PB15, PC6, and PC7. PC8, PC9, PA8, all the way through PA12. PA13 is SWDIO. That's the ST-Link programming I/O pin. It is a 5-volt tolerant pin, but I don't want to use that one because we use that for programming. The PF6 is the next one. PF7. Actually, PF6 can also serve as ground, so I'm gonna eliminate that one. PA14 is a programming pin as well, so we're going to leave that one alone. And that's the SWCLK, that's the clock. PA15 is one of them. PC10, 11, and 12. PD2, PB3, PB4, PB5. PB6 and PB7, those are the FTF, the fast mode pins. So we're going to leave those alone for the moment. So are the PB8 and PB9. And that is it. So let's take a look at pins that we can use that are 5-volt tolerant. And we have a pretty good number of pins that we can use. Just for the heck of it, I'm going to color the ports just so I know what port I'm looking at. So we'll start with the port F. Okay, that's all the port Fs we have. So let's go to port A or port B. Let's do port B first. Okay, the next one, let's do port C, port A, and finally port D. It looks like there's only one port D. Okay, so we have color-coded our pins for the ports. It looks like we have the most in the port B and port A. I think port B is our best bet. It doesn't really matter if we use multiple ports, but I was trying to find if there was any way we could get some consecutive, and we can, but I think it's probably a better learning experience if we go with separate ports and pins just to give ourselves a challenge and send a byte over multiple pins and ports. And I kind of want to put them pretty close together, so maybe I'll use from 40 to 33. So let's check what alternate functions that I can use with that I may want in the future. Okay, so 33 through 40. This is a timer. We have timers all over the place, so that's fine. 33 starts here. There's SPI. There's an event out. There's a UART3, 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 timers, SPIs. Looks like I'm pretty safe if I use these pins. So I'm going to go ahead and do that. So I'm going to attempt to use these pins here. So what I'm going to need to do is, let's say we're using the letter A, and I need to deliver the letter A, a character, to these pins on, they're going to be 2 different ports and 5 pins on one and 3 pins on the other. This should be PCs. This should be another color. Let's say we're going to take the letter A. The 1 would have to be sent to this bit 0 at PB12, a 1 sent to the 7th bit, and then a 0 sent to the 8th. And to verify this, I'm going to put an LED on each one of these pins. This may seem like a lot of work, but it really does allow us to verify that we're sending the correct information to these pins, and they will be delivered to the LCD correctly. We're going to be focusing on pins number 33, 34, 35, 36, 37, 38, 39, and 40. We're going to put a resistor between these 2 tie strips here. For example, number 33, we'll put a resistor, a 330 ohm resistor from this point to this point. Then we'll put an LED from this point to the ground rail. Since the LEDs have such a large LED portion of it and the tie strips are pretty close together, these LEDs will get in the way of each other, so I went ahead and bent the leads in a way that the main LED can be staggered. These are all in the same direction, where the anodes are all on one side and the cathodes are on the other side. So let's go ahead and plug the resistors and LEDs into the circuit.
Okay, so all of the LEDs are wired up through resistors to the pins that we need to test. So let's try it out.
First thing I'd like to do is make sure all of these LEDs are working. So I want to output a 1 to each of those pins, port B and port C. The first thing we need to do is set up each of those pins for output. And we're going to be using the mode, type, speed that has a pull up or pull down resistor. And then we're going to just output a high on each pin. What do we need to do first for setting up the microcontroller? We need to first set up the RCC, which is the reset lock and control register for the advanced high performance bus. So let's go ahead and do that. We're going to set that for port B and port C. We're going to be setting up each pin, which is 8 pins for out. It would be very tedious for us to add the mode, the type, speed, and pull up, pull down for each pin individually. So there's a couple ways we can do it. We can put it into a function and we can pass in the pin numbers and then run the function each time setting each of the pins. But I would like to do this in a different way. We can take a look at the registers, the mode register for port B. We can plug in where we want the 1s and the 0s and just put in that number. So let's do that for the mode register first and see what's involved in doing that. If we were just wanting to set one pin for the mode, we would start off with going to the register, the mode register, and we would do an ORing of the first bit because we want a 1 in the first bit. And then to put a 0 in the next bit, or the second position bit, we would do an AND and a NOT for the second position. What we've essentially done with those 2 lines of code is we've put a 1 here and we've put a 0 in this position. So we're looking at pin number 12. Since this is one 32-bit number, we can just go ahead and put the 1 and 0 here for the pin number 13, the 1 and 0 here for pin number 14, and the 1 and 0 here for pin number 15. And then just put zeros in the remaining slots. So now we have an actual number we can just plug right into that register. Let's put this number into the mode register as a single line. So we're going to remove the second one and we're just going to put a number in this place. We can write binary notation just by using 0B and then the number. So we know that that's going to be 0, 1, 0, 1, 0, 1, 0, 1. And then the remaining will be 0. So we need 2 more sets. So that should be the number. You can see that this number is really long. So let's take a look and see what this number would be in hex. I'm just going to use a simple online converter. We can see that it's 55. So let's take that number, plug it in here. I'm just going to put it into a comment so we can use it later if we want to. So let's go ahead and do the rest of the registers that we need, the type, speed, and pull up, pull down. So let's take a look at the type register. This is a single bit register, so we don't need this top portion at all. And we can see that the reset value is just 0, so we can manipulate this however we need. So we're going to be using the output push-pull, the reset state. We're not going to have the open drain state. So 12, in fact, this is going to be 0 all the way. So we're just going to put a 0 in this register. And we can just use the decimal notation for this. It doesn't really matter. Let's take a look at the speed register. We can see that there's a reset value for A, so we're not really worried about that. And the reason why you have the port A reset value is because of the programming pins are on port A, and that's setting those programming pins for that function. You can see that it's also in the mode register, the same location. The programming pins I'm talking about is the SWCLK and the SWDIO. Okay, so we're looking at 12, 13, 14, and 15. Okay, so we need these pins. We're going to go ahead and just put high speed. It doesn't really need to be high speed, but I'm just going to do that as my own default. The speed register, we have all 1s in that location. I'm just going to take this number that I have here, and I'm going to convert it to hexadecimal just to see what it looks like. I'm just going to replace the 0s to 1s since we're looking at 1s in those spots. And it looks like it's FF, which makes sense. So we can go over here, GPIOB speed register, it's O speed. And to put it in hex, you have to put a 0 and an X before it. We can do this in binary as well. And I'm going to do the same thing with this one. I think it's easier to read personally, so I can just go over here and put in the 1s. I could do this one here too, but it really isn't necessary because they're just all 0s. All right, so let's look at the pull up, pull down, and we're going to use no pull up. It's going to be 0. So since this is 0, we can just put a 0 in all the positions, which means that we can just do the same thing like we did on the type. Actually, we don't want to do that. We want to just use the equals. Duh. Because the OR will actually not produce the correct bits in the places we want them. So we have just reduced the code considerably. We could have had this 4 times. Let's do this for the port C now. Just going to do a copy and paste and replace all these with C's. And obviously these numbers are not going to be the same. So let's take a look at what we need to do there. Let's take a look at the mode first. So what pins are we using on port C? So pins 6, 7, 8, and 9. So pin 6, 7, 8, and 9. That's going to be 0, 1s. And all these are going to be 0s. Now I'm going to set up something that makes it a little bit easier for me to see which positions I need to set. 9, 8, 7, and 6. And it's 0 and 1. So this would be the binary number. So let's go ahead and copy and paste it here. Take out the spaces. All right, now we can do it to this one. And the speed would be the 1 and the 1. So I could have just copied this one and put it down here and just put this 1s and 0s, but this is a little bit, for me, it makes more sense to do, just so I don't have any errors. Okay. All right, so we've set both of our ports and all the pins that we need to set for output. Now we need to turn on all the LEDs. To turn the LEDs on, we're going to have to set those pins high. We're going to use the BSRR register, which is the bit set and reset register. To set the pins, we need to put a 1 in the bit set location. And the port we're working with right now is port B, 12, 13, 14, and 15. Let's do that first. So we have that here, 12, 13, 14, and 15. And to reset those, if we ever wanted to do that, we would put a 1 in these locations. So let's go ahead and see what we need to do to set them. Just put a 1 in these locations. The 0s would be in these locations. 16 more. So we're concerned with these positions here. To reset these pins, you'd want to put 1s here. Let's look at what we need to do with the port C. So port C, we're using 6, 7, 8, and 9. So we want to put the 1s here. So we have 0s all along here and 0s in the beginning. Okay, you can see the 2 lengths are the same. So we have the correct number in there. And just hopefully we have them in the right positions. Theoretically, we should be finished with the program. And you'll notice that all of the LEDs are lit up. At this point, we don't really need this anymore because we're just using this as testing. These are the bits set and reset register, and we're just turning on the bits just to see if they work. So we can delete that. Let's create some pseudocode so we can know what to do in our program. So let's send a character or a byte to port C and port B. To be able to send a byte to disparate pins and disparate ports, we'll need to send bit by bit from the byte, from the character. So we're using the character A, and that's 0, 1, 5 zeros and a 1. And that's the byte represented as a binary notation. So you can see that we need to send each of these bits to the respective pins that they're going to be going to. And port B will be the first, port B will be these sets of pins, or these sets of bits. And port C will be this set of bits, because that's the way we set it up in the circuit. This will be 12, 13, 14, 15 on port B, and this will be 6, 7, 8, and 9 on port C. We need to test bit number 0 on the byte and send it to port B, pin 12. And we need to do this for each pin. And I'm writing it in longhand right now because by writing it in longhand and showing each test of each bit, you'll get an understanding of what's going on. And then we'll take that and we'll put this in a function. So all we're doing is we're putting the letter A to that function, and it automatically sends it to those pins and ports. Well, first let's actually set up a character. So let's call it a car. Character is equal to A. And this A is actually equal to this binary number. So we're going to be testing for this number first. But how do we test a single bit in a byte? That actually seems quite difficult to do, but it's not. We're just going to use bitwise operations and a mask to determine what this particular bit is out of this entire byte or this entire character. What we're going to do is we're going to take a number for the letter A, 0, 1, 0, 0, 0, 0, 0, 1. And we need to find out what this one is. So we're going to use a mask, which is putting a 1 where we want to figure out what bit we want to test. So the mask looks like this. And we are ANDing. This is a bitwise operation of AND. And the AND truth table says that a 1 and a 1 is going to always be a 1. A 0 and a 0 is going to be a 0. And a 0 and a 1 will also be a 0. So now we know that we have the number 1. So this is a true. So how do we write this in code? We're going to use that and in an if statement. So if the character, which is the same thing as saying this, and the mask of 0, 1, 0, 0, 0, 0, 0, 1, that's the same thing as saying this. This is the character, and we use the and we have our mask for the character or for the bit that we want to test. So in that case, we know that we're going to get a true result. So what do we need to put there? We need to light up that LED because we know this is going to be a 1, only if it shows true. But we also, if we have A here, we know this particular one is going to be true. So we'll use the bit set and reset register for B, and we're going to or equals, because we're going to be setting it. We're going to be putting a 1 in that bit, and we're going to use the bit set part of the register. And this is going to be number 12. If this position is a 0, then we want to reset that bit in the register. And for resetting it, you might think that we want to do the and not to take the bit out of this or make this a 0. But we don't really want to do that because we're going to be putting a 1 in the bit reset register, which will automatically reset the bit set register to 0. So we're using the bit reset and then 12. Now let's move on to the next bit. So this would be bit 0. So bit 1, using the same number, 0, 1, 0, 0, 0, 0, 0, 1. We're going to and our mask will look like this. You can see that the one we're going to test now, bit number 1, has the test bit in the second position. So we can do the arithmetic, the bitwise operation, and we know that 1 and 0 is equal to 0. 1 and 0 is equal to 0. So that is a correct determination of this second bit. It is a 0. 0, 0 is 0. And 1, 0 is a 0. So now this is equal to false. So in this case, this particular bit and pin will not be lit up. It will not make the LED shine. I'm just going to copy and paste this code because it's the same thing. You can see that we only need to change a few things on this code, and that allows us to understand that we can also create a function to do the same thing. So we're creating the mask. This is not the right mask. I should be putting a 0 here. So we're creating a mask where the 1 is in the second position. In this one, it was the first position. So we're going to do that for the rest of the B. So the next one will be the third position, or bit number 2, and this will be affecting pin number 14. And we have one more port B to test. So it'll be the fourth position, or bit number 3, and this will be pin number 15 for port B. And now for the C. We're doing the same thing, we're just going to be changing the B to a C, and the first one is pin number 6. This is the position number 5, bit number 4, and this will be affecting pin number 7 on port C. I have 2 left to go. Okay, and then 1 left, 1 remaining, which is the seventh bit. I think I had 1 too many bits here. No, I must have. That's the first, second, third, fourth. There we go. 5th, 6th, 7th, and 8th position. And then you change this to 9 because that will be the last pin we're using. Let's confirm those pins. 12, 13, 14, 15, and 6, 7, 8, and 9. Okay, so there's a lot of code cleanup we can do here. You can see there's so much code here that it starts to get unwieldy very quickly. I just want to show this as longhand so you can see what is entailed in delivering a single byte character. So let's go ahead and test it and see if it works. Build errors. I shouldn't have used the quotes. So used to using quotes in C#. So use a single quote for the car data type. Let's try it again. Okay, no errors, no warnings. Now we can download the code to the microcontroller. I just noticed something that I did wrong, and this I'm showing in just regular binary notation, but it's not code-wise binary notation. So I have to put a 0B in the front of each of these. You can see how this longhand code, repeating everything by hand, can get really error prone and messy. Okay, now let's do that again. Okay, the microcontroller was programmed, and you can see that bit 0, the bit position 0, the first position, is a 1 like we would expect. And then the second, third, fourth, fifth, sixth, those are all zeros, which is correct. And then you have the second to the last one, or the 7th position, is a 1, and then the 8th position is a 0. So this shows the letter A correctly in binary format on the LEDs. First thing I'd like to do is create definitions for these bits. This will also help us understand how the circuit is connected to with the microcontroller and the LCD. So which pins and ports go to which data pins, and the enable and read write and register select. So let's set up the defines up here. I want to create something very understandable in the way that we have the circuit wired, and that would be LCD D0 through D7 would be my names for the define. So let's call this one LCD D0 pin, which will be 12, and we can define the LCD D0 port, which will be GPIO-B. We'll do this for each connection, so we can just do a copy and paste. So the next pin is number 13, and it's also B. That's going to be D1, D2 on pin 14, port B, D3 on pin 15, and this is port B. And now for the port C, D4 and pin number 6, 7, 8, and 9. For D5, D6, and D7. And the pins that I'm referring to are these pins, 12, 13, 14, 15, 6, 7, 8, and 9, going to these LCD D0, D1, D2, D3, D4, D5, D6, and D7. So it really tells you how the circuit is put together. And if you need to make a change in the circuit, all you have to do is change the pin for the D0, which pin it's going to go to, and what port it's going to go to. And none of the program will have to change because it'll always be set here. And the program will use these defines within the function. So we're going to take this portion and put it into its own function and use those defines in that function. Instead of making a prototype, I'm just going to go ahead and make the function up here. At this point, I don't think it needs to have a return. So I'm going to have void, and I'll call it send bit to port and pin. And I'll have some inputs to this function, and it's going to be, if we want to pass in the ports, we can get an idea of what the data type is by just hovering over one of the ports. And you can see it's GPIO type def, and you'll see it's a pointer. I'm just going to do a copy and paste of this, and then the pointer I'm just going to call it port. This will be the actual variable name. Okay, so the next thing we're going to be bringing in is the actual pin number. This number is only going to be a pretty small number. I'm just going to use an int for this. And then we actually have to send the bit, whether it's true or false. So we'll just call this will be actually I don't think I can use bool in this language. Use an 8-bit integer unsigned, and it will be, so I'll call it bit state for now. I don't know of a better variable yet. So we'll just take this condition and we'll copy it into that. All right, so we're going to replace the port here. So instead of using the port that we had hard-coded, we're going to pass it in. And then this, I think we're going to use the bit reset register. So we're going to try, because you can see this number is at the 4th position, 0, 1 to actually the 3rd position. And this one is actually all the way over here. So we want to use the same number, pin number, in the same way. So what we can do is we can actually just take out this S, and we have a BRR, and you can see it's at the same position because this is the bit reset register, and this is the bit set and reset register. And the bit reset register is only a 16-bit. It only uses the first 16 bits. And the bit set reset uses all 32 bits, but the bits 16 through 32 are the reset. Okay, so now we have to change this to the reset register, and we're going to actually put the pin number here, and we're going to use the bitwise shift operation and remove this number. So by putting the pin number, let's say 12, it's going to put this pin number into the 32-bit number at the position. So if the pin number is, let's say 9, it is going to come over here and go 0. It's going to left shift it. So it'll actually put a 1 right here where we want it, which we did for the setting and resetting when we were lighting up the LEDs initially. And for the bit reset, we're going to do the same thing. We don't actually have to make any changes to this portion of it because we want to reset at the same pin number since we're using the bit reset register and not the bit set reset register. Now the only thing we have to change now is the condition, and this is going to be the bit state. So we have created a much more tidy code for this bit of code here. So let's go ahead and invoke that. I'm just going to take my prototype function and I'm going to copy and paste it here. And for this one, we're going to use port B, GPIO-B, and we're going to use pin number is going to be 12, and the bit state will be this. Let's see, why doesn't this work? Oh, I have the void here. Okay, so this does the same thing as all of this. And we have made it so, actually, I don't want 12 to be there. I want to use the defines. So the define would be, this would be for the port and the pin. Okay. That's what I really want. The D0 pin will be 12. You can see that it says here. And then the port will be the port for, it's really difficult to read in this way, but you'll see that the 0, 8, and then the 4 in this position. If you look at here, should show the same thing, the 8 and the 4. Yeah, so it's the correct port as defined here. Okay, so we can go ahead and erase this portion of it. And we're going to just do a copy and paste of all of these. We should have 8 of them. This should be D0, D1, D1, 2, 6, and then the last one, 7 and 7. This is going to have to change as well. So we'll have the masks going up in bits. So we're testing for this bit within the character. We're testing with this bit with the character, this bit with the character, and so on down the line. So we have just taken out a lot of code and made it much tidier and more readable. Now we can also tidy up this. We can put this in its own function, and we'll do that as well. But I want to test this to make sure it works first. And as you can see, we have the same result. The 1, 5 zeros, and then the 1, and then the 0. Generally, when we're sending characters or commands to the LCD, we do that in one line. We also send an entire string of text in one line as well, but we'll start with just sending character by character as one-liners. So we'll create a function that sends the entire character to all the pins of the LCD. This should be very straightforward. So let's start with creating a function. This function is not going to return anything, so we're just going to use void. I don't think it's going to return anything at this point. We're just going to say send a character to the LCD data pins. And then all we're going to be putting in is the character. And over here, we're using a car, so we'll use that as a data type. We'll call it character. Now, all we need to do is actually take all of these and just move them into that location. So we have the character and it's being pushed into these lines. And to invoke that, we're just going to copy this line. And instead of putting character here, we could just do this, but that would be a waste of an entire line of code. So we're just going to put in the actual character in that line and remove this line that creates a variable and then stores the A into that variable. So now you can start to see how easy it is to actually just take characters and then send them to the LCD. I want to start by creating a function. This is going to be a non-returned function, and I'm going to call it set port and pin for out. And then what we want to bring in is our port and our pin. Let's see how we want to do that. I'm going to steal some stuff I had here, which is going to be the same thing because we're using the same defines. Since we're really focusing on a single pin in this function, we only care about the port and the pin number. Since we're going to be setting each pin one by one. You can already see from the first video of this LCD series that I told you to do it this way. This is one alternative way to shorten the way we're doing it as the longhand way, where we're setting the mode individually, the type and speed and pull up, pull down register. We're doing that individually for each pin. We're going to go back to that, but still it's going to be a much easier and clean code because we're going to be doing something very similar to this, but we're also making it so it's reusable because it's using the defines, and we can change only this if we need to change our circuit. So instead of using, let's say 9, we need to use 10 on the GPIO for C, or we need to use another port. We can just make that change and the entire program should work flawlessly. So let's take a look at these one by one. We're going to look at the mode. So let's go ahead and just type in port, and we're going to go to the mode register. We can see down here we want a 0 and a 1 in the mode register. And this would be position 31 and position 30 because this starts with position 0. So how do we get to that position when we're talking about pin number, say, 15? Here you have all of the positions for a 32-bit number. The row on the bottom represents the positions associated with the pin number, since the mode register requires 2 bits per pin. So for instance, if we're working with pin number 15 and we have to put a 0 in this position and a 1 in this position, we need to figure out how to use the left shift operator to make this happen. In this case, we're going to have to do a left shift. The 1, actually it's an AND equaling a NOT,
1 left shift and the 31 position. And in this particular case, we need a 1 in that position. So this was going to be an OR equals a 1 left shift in the 30th position. So for the case of the 0 in the 31st position, remember there may be a 1 here because of some other task that we had to perform in another part of the program. So we want to make sure that there's a 0 in this position. And the way we do that is we use the AND not 1 left shift 31, and the 15 is what we're given. So what times 15 plus what would equal 31? That would be times 2 plus 1. So we're multiplying 15 times 2, which gives us 30, and we're adding 1 to give us 31. The 30th position, when we're given the number 15, is actually easier. It's just 15 times 2. 15 times 2 is equal to 30, so that one is pretty straightforward. Let's say we were given pin number 10. 10 times 2 is equal to 20. That would be putting a 1 in this position, and then 10 times 2 plus 1 would be the other position, which is the same as this example. Okay, so we're going to apply two operators here, an AND and a NOT, and an OR. The AND and a NOT for the 0. So let's go ahead and do that one first. AND equals NOT. I'm going to put it in parentheses just to make it a little bit more readable and contain it. 1 left shift, and we're working with the pin number here. This is what we're given. So we'll start with the pin number, and we multiply that by 2, and we add a 1. For the next one, we're going to use an OR bitwise operation, and we're not going to add a 1 to it because we're not looking at the second position. We can do the same thing with the speed register because that's also a 32-bit number. So I'm just going to do a copy and paste here for the speed. This is where the information using the left shift and all the detail that I've given in the AVR series of microcontrollers and programming, this is where this stuff comes in really handy. So if the left shift and the bitwise operations and all that stuff really confuse you and you're not understanding it, I highly recommend going back to the AVR series and checking out those videos. Because really, you're doing exactly the same thing. All we're doing is manipulating numbers within registers. It's just like going to a large control panel and just switching switches, the ones that we need to use at the moment. So in this case, we're just doing the ORing on both of them because we need a 1 and a 1 in both positions. Since we needed a 0 in the other position, we needed to do an AND and a NOT. For the type register, we're going to be doing the AND and NOT. Now let's just rewrite it. Port, the O type, output type is going to be an AND equals NOT because we want a 0 in that position. We'll use the left shift bitwise operation, and we're going to be using the pin number straight. So we're finished with the type, and the pull up, pull down looks like it's the same thing. So we'll just do a copy and paste. PUPD register. I'll put a space here so I can read it. To execute all of this, we're going to have to use it in the main part of the program. And for the port, we're going to do the same thing as we did over here. The LCD D0 port, we'll start with that one. The LCD D0 pin. We're setting the port and pin for output for the D0 port and the D0 pin. Very simple. We'll do that for all of them. And we'll just replace these with the appropriate numbers. 0 through 7, we'll do that to the pins. Just as an aside, in this case, we have two lines. We can just put it into one line just by separating it with another OR because they're the same operation. They're both ORs. Okay, so we have all of our pins set. We can actually remove these, but I don't want to get rid of them yet just because in case this program doesn't work, I can use this for debugging. So I'm just going to comment out these for now. So let's take a look and see if it works. Okay, we do have an error, so let's take a look and see what we have. And this is really good. It's catching us on some simple math computation errors, because if I did a pin number multiplied by 2, I would get, say, if I started with 15, I would get 30, and then I added 1, and I would get a 31. But if I did 2 plus 1 first, which is 3, 15 times 3 is definitely not 31. That would be 45. So it's actually saying to contain the parentheses around the plus, but I would rather actually contain this. So it does this first or separately than the 2 plus 1. So let's go ahead and do that. So we're going to do it on all the instances where we're doing mathematical computations within a left shift. We're going to contain this portion. Let's see if we only need to do that. It might ask us to contain the entire thing as well. I'm not going to contain this because this order of operations would be fine. Let's go ahead and build and see what it says. It's still saying to do the same thing. So I'm going to go ahead and contain all of it. Okay.
Let's try it again. Okay, we have no warnings. That's good. And the build is successful. So let's go ahead and program the microcontroller and see if we still have the letter A outputting to our pins. The microcontroller has been programmed, and you can see that the correct pins have been output as 1s and 0s. You got the 1 and then the 5 zeros, a 1 and then a 0. Let's go ahead and replace that A with a B and see what happens. Okay, so let's take this and put a B here. You can see that these two pins changed because the lowest bits, the first 2 bits in a change from a B to an A is only going to change from this being a 1 to this being a 1, because that would be 2. This would be 1, and then putting a 1 in this position would be a 2. A 3 would be both of these lit up. So a C should cause both of these LEDs to light up. So let's try that. Let's change this B to a C. And it looks like we got exactly what we expected, as these both lighting up to equal a 3. This one is of course going to stay the same unless we went way higher up in the ASCII code. I think at this point it's probably safe to go ahead and get rid of this. I can delete that since I know that the program is working. There are a couple of things that I still want to do with the program before we get into the actual looking at the LCD and looking at the timings and seeing what we need to do with the enable, read write, and register select and the data pins. And that is, we haven't really done anything with the reset clock and control register and making this automatic. Currently, we have to manually enable the GPIO-B and the GPIO-C ports. But what if we use another port? You know, we can, if we just use these 2 lines here and only enabling B and C, we can only use B and C in these defines. So let's take a look and see how we can make this more automatic. The idea that comes to mind to figure out how to determine the GPIO according to this address or this designation is to put it directly into this portion or this function. Because what we're doing is we're specifying the port here, and it could be any port. So we can put a condition: if this particular port is equal to, say, GPIO-B, then we invoke this particular one. So we're going to have to do this for each port. So let's go ahead and try to do that. I'm going to go ahead and do a copy and paste. And I want to do it at the beginning because I want to make sure that I'm setting the reset clock and control register before I actually change the output state or the state of the port itself. But I also want to do another thing. Let's start putting the condition in first. Let's say if port is equal to GPIO-A. Let's do that first. Let's give some space here. Then I'm going to want to put the A here. But I think I also want to figure out if it's already done, if it's already set. Although actually I'm not really sure that's necessary. It doesn't hurt anything to actually just set it, because we need it set anyway, and we can do it every single time. Even though it's already been set, we can set it again, or just make sure that there's a 1 here, which is what we're doing anyway. Let's do this for each port. We'll do that for B, we'll do it for C, and D, E, and F. And if your controller has more ports, then I would add more here. Let's actually see how many ports there are on this particular one. Okay, so it looks like there's A, B, C, D, and F. There's no E. So I'm not going to be able to do this E here. Yeah, see, it doesn't. I put the E inside that to change it, and the options it gives me is all of them. So it's telling me that there is no GPIO-E, so pick from any of these, because that's the closest match. So I'm going to use the F. And with this change, we should be able to remove it here. So I'm just going to put some comments here just in case we still need it. And now what I want to do is put this into a function. I want the actual main to be very minimal and only calling certain functions to initialize the ports and to actually send the characters. Let's make another one here. I'm going to call it initialize ports for LCD because this is going to be under the LCD header file, and if we have to initialize other ports for other services or features, we can name it for that. There's not going to be anything passed in, so we'll just leave that blank. And then we're just going to take this and move it up. And we want to initialize the ports here. Okay. All right, let's see if this experiment works. I'm going to just do a quick build just to see if we have any errors. It looks like we have an error. GPIO-E is undeclared. You see, we know we don't have a GPIO-E, and that's exactly what I thought. And we actually didn't change it here, so let's just change this to an F. And we should be okay. So you can see what we had in the beginning is the letter C. So let's go ahead and flash it and see what we get. And I see it right here. We're putting it in the wrong function. The function we're putting it in is where we send the bit to the respective pin and port and pin. That's not where we want to put it. We want to put it where we're doing the initialization of the port itself. So we're going to cut it and move it into the set port and pin for output. I generally put initialization stuff at the top and I put other functions below the initialization. So in my habit, I looked at the very top and I saw something with a port in it and I put it in that location. And it looks like it works. If you look at the program, we don't have much in the main anymore. We have very little. We can actually take all of this stuff out right here and you can see how small our main code is. We have pretty much everything above the main, and we can take all this stuff out. We don't need this in this program at all because we're going to make a header file for the LCD. So let's go ahead and do that. The main.c will be under the app. So we're going to select the header extension, call it LCD functions. You can see another file was added called LCD functions, and there's no code inside this. The first thing you want to put into this LCD functions.h in every header file that you make is using the if not defined statement, and then you want to end it. And this is a directive or a condition that I'm going to implement that will only allow the function, the LCD functions, to be executed once. Because we could have the LCD functions header file in many other files, many other sub files or other header files, other C files, as we make larger and larger programs and more sophisticated programs. We only want all that code that's within this, if not defined, to run once. So the way we do that is we create a define, and we're going to call this program something, LCD functions header. And we have to copy and paste that specification, that identifier, to the if not defined and the name of the define. And then all the code that we don't want to run more than once will be in here, because what it's doing is saying if the functions header is not defined, then define it, run the code, and then now it's defined within our entire solution. So now we can put the actual code within this location and it'll only run once. So let's go ahead and cut the defines and paste it in. So now these defines will only run once. I'm going to do the initialization first. That's why I wanted to do it one at a time. So set port and pin for output. That's going to be the first thing I want. And this is not because they have to be run in a certain order. It's because for me, it helps me understand and make the code more readable when I put the initialization at the top and I put the simple functions after that and then the more complex functions after that. The initialize ports for LCD, this is a little bit more complex than the actual specific function to do that. So we have the initialize ports for LCD. Now we're going to go to the next one, send a bit to the port and pin. We're going to cut that and paste it here. And then we're going to take the last one, which is the sending a character to the data pins. Takes advantage of the function we just created. Cutting that, we're pasting it here. So this is the beginnings of the LCD functions. Go ahead and save. We need to include the LCD functions. So now we're including all of the code that we have here a single time. So let's go ahead and try it. And it looks like it still works. So success. Let's go ahead and put a D in there just to make sure that we're working with the right program. And okay, good. You can see that the A, B, and C use these two pins, and then D is 1, 0, 0. So that makes a lot of sense. I'd like to take a look at controlling the LCD by using the timing diagrams in a specific way. Here are the timing diagrams that I'd like to look at first. You have the LCD write operation, and you can see you have the enable, you have the read write, and you have the register select. And you can see that you have the actual high or low signal, and you have the required timings between when that signal has to be high or low with respect to other signals. For example, the enable cannot be used until the read-write goes low, and that a certain amount of time has been passed before the enable is high. And the same thing with when the enable goes low, a certain amount of time has to pass before the read-write can go high, or before the register select can change its signal state. So before we do an enable, the TAS, the RS, or the RW, the read-write or the register select, The register select or the read write must be changed before the enable. So let's take a look at the TAS symbol for the write operation. And most of these units are going to be in nanoseconds. And I think I want to write it in this way too, so I can write it as if it's code. So this is the position where the read-write or the register select must be changed. The read-write must be either on idle state, which is low, or it must have gotten from the high state to the idle state. The register select must have actually gone from low to high or from high to low before the enable goes high from its normal state of low. So I'm going to put in a sort of a dimension between here. And the TAS must be a minimum of 40 nanoseconds. So this is 40 nanoseconds. Okay, so the TER, the symbol TER, is the enable rise and fall time. I'm not going to worry too much about this. So the time the read write and register select where the enable is on, and then to where the enable is off, which is the PWEH. And the PWEH has a minimum of 230 nanoseconds. Now we know how long the enable has to be on. Actually, no, there is a number here. It's TEF, that's actually a maximum. The TER and the TEF, the TER and the TEF, these two here has to be a maximum of 20 nanoseconds. So we can't have it going from low to high more than 20 nanoseconds. But we really don't have any control of that, so I'm not going to worry about that. So what I want to do is take a look at the next required timing, which is when we can change the data bits from a high or a low, or start writing the data to the data pins. And it looks like we just need to make sure that the enable is on when we start writing data to the data pins. So I'm going to erase this 230 nanoseconds. I'm going to put a line and I'm going to say at these points turn, and over here I'm going to put read write low and change register select. So first we have to make sure that the read write is low, and then we have to also change the register select at the same time, and then we wait 40 nanoseconds, and then we can turn on the enable. While the enable is on, we can start writing the data. It appears that the value here doesn't actually need to be set, or we don't have to wait any specific time. We can just start immediately sending the byte or the command. We have to wait a certain time after we start or after we output the byte that we can turn off the enable. So let's take a look. What is that DSW symbol? That is a minimum of 80 nanoseconds. So now we can turn off the enable after the 80 nanoseconds. After we've turned off the enable, we have to wait this long, the TH, before we can send any more information on the data pins, or before we can change the read write or the register select. Looks like TH and TAH are the same. Let's see what the differences are. TAH is 10 and the TH is 10. 10 nanoseconds. So this is 10 nanoseconds. So we know we have to wait 10 nanoseconds before we modify the data pins, or we change the read write, which is going into the read mode, or we change the register select. Actually, because the read write is always in write mode during the sequence, we shouldn't say change, we should say bring read write high. And then we have a final requirement here where we can't bring the enable high again to do another operation, to start another cycle. And this could be either a read cycle or a write cycle, because you'll have the read operation. You're also doing the same thing with the enable. You're bringing the enable high and then you're bringing the enable low again. And you have the same symbol called TCYCE, enable cycle. And for both of those, it's 500 nanoseconds. So in this section here, we have approximately 130 nanoseconds. So around here, you're going to want to wait probably around 400 nanoseconds minimum. I plan on putting the LCD along this area here, about 14 pins. On the breadboard I have, including these two LEDs, 14 and 15. So I do have enough pins here. So the register select could be the first one. So the read write would be the next LED. Enable would be the LED that's on this pin here. And then after that, we can have these pins from D0 to D7 along this side here. We're using the pins number 33 through 40. And 33 is at this location of the breadboard, 33 and 34. So we'll need 3 more pins And I think 41, 42, and 43 would be fine since they are also the 5-volt tolerant pins. I'm going to go ahead and apply some LEDs to those pins, and then we can test the enable, read write, register select, and the byte again. So let's get started. And I'm going to take these completely out, and I can easily just connect this VDD to this one here. So let's connect the VDD on one side to the VDD on the other side. Now we need to take the ground and put it to the ground rail on the other side. So we have the positive going to the positive, and we have the negative here going to the negative rail on the other side. So we have the positive supply, pin number 32, going over from this tie strip to number 11 tie strip and going to the positive rail. And we have the ground, number 31, pin number 31, going to tie strip number 10 here, and then going to the negative rail. Now we have more than enough space to put the LCD in. There, I'm going to go ahead and turn this on just to make sure that it has the last thing that I programmed and everything works as expected. We can go ahead and try putting another character. Let's go A again, compile it, and then program. Okay, it works. Now I'm going to add 3 more LEDs to this location. I'll probably reassign the pins where I'm outputting the byte to these pins here, and then reserve these 2 pins and the next pin here for the enable, register select, and the read write. Since we use defines, it should be pretty easy to reassign them. I'll go ahead and add 3 more resistors first, and we'll add 3 more LEDs. It's kind of hard to see which one is in sequence. I could share some holes on the negative side. Now that we've done that, I'm going to plug it in again just to make sure it works. And it works. Program, we'll go to the LCD function .h. Since we need to adjust the pin numbers, let's take a look at what new pins we'll need to use. We're going to be using 8, 9, and 10 on port A. So this will be for the byte, enable, read write, and register select. So we'll make this one for enable. This one will be enable, read write, and register select. The D0 pin is going to be going to GPIO B15. So D0 is going to be 15 on port B. D1 will be 6 on port C. 2 will be 7 on port C. And this is going to be 8, port C, 9, port C, and then we have 8 on port A. 9, port A, 10 on port A. Now let's set up our enable, read write, and register select. So we're going to put in 3 more defines. LCD enable, and we'll make that one 14. Wait, this is pin. Let's say the E pin. 14, and E port will be GPIO-B. So let's do the read write. Pin is going to be number 13. Read write port will be GPIO-B again, and then the register select is the last one. Pin number 12, port, and that's B, and the port here will be GPIO-B. Now we have the defines complete, hopefully. We can go ahead and initialize the ports for the new pins that we have. We should have 3 new pins. I'll go ahead and just do three of these. The enable pin, I'm just going to do a copy and paste. Enable pin, and then enable port. And we have the LCD read write port, read write pin. And the last one is register select port and the LCD register select pin. And we're just enabling those pins on the microcontroller to be set for output. Let's just see if those pins work. We'll light them up and make sure that we have correctly assigned the pins. We should get the letter A again as an output, but in different pins instead of the pins that we used to have. And then we should also see the enable. Let's go ahead and make the, we'll use this one, and we'll just set them to output. So we'll put this in the main.c, and we'll just manually set them to output. So let's do LCD enable port, LCD enable pin. And we'll just put a 1 here, true. Read write port, read write pin. Set a 1, and LCD register select port, and LCD register select pin. And since we're just putting 1 here so we can light up the LED, looks like we got the correct output. These 3 pins we wanted on, this one, and this one. This is the register select, this is the read write, and this is the enable. Those 3 are on. And we have the A, which is a 1 in this position, a bit high in this position, and a bit high in this position. So we have the correct output. Now let's turn these off just to make sure that we have it set correctly as well. Actually, I'm just going to comment out those so they won't be executed. We have the correct output showing just the A, and those are off. We can test the timing diagram and the code that we have to create. I plan on setting the read write and the register select. The register select is going to set between either writing a character or writing a command. So we're going to set the read write, change the register select. We'll wait the 49 seconds and then turn on the enable. This will be in one function that I think would be most appropriate put in that function. We already have an output byte function, so all we really need to do is add the turn off the enable after 80 nanoseconds in that same function. So we can bring those together. So this one will be setting the read write, setting for read or write, or and register select for character or command. In the next one, we'll be outputting the byte and simply turning off the enable. Now I'm going to also add this 10 nanoseconds in this function as well. So we definitely need to wait 10 nanoseconds until we do any more modification with the data pins or modifying the read write and register select. At first, we're just going to have this stuff running really slow so we can see it on the LEDs. And then I'm inclined to hook it up to the LCD to output some commands and characters and see if it works with just a slightly faster speed, because all of these numbers are minimums. And that way we may not have to read it to check to see if the LCD is busy. And we'll go faster and faster to see at what point it breaks, if we get to that point. But because we haven't gotten into the timing section of the microcontroller, we really can only use sort of just a time delay of our own choosing. So let's create a time delay within the header file. Put it up at the top. I'm going to call it a non-exact time delay. Pass in an integer of time delay, and we'll just do a loop. So all we're doing is we're creating a for loop with the actual time delay number here, and the integer can go pretty high. So I'm not sure, I don't think we have to put anything in here, but we can later on if we have to. Okay, so let's go to when we're sending the character, let's go ahead and put in the turning off the enable. So all we have to do in this case is access the enable port and then access the enable pin, and we're just going to put a 0 in here because we programmed it so if the bit state is a 1, it will set it, and if the bit state is 0, it will reset it. We need a time delay here, so let's go ahead and, since I automatically thought it would be not exact, I'm going to go ahead and put a not exact time delay. We'll just put 10,000 in here for now. And what we're doing is we're putting in this time delay here. Could put like 80,000 just to see what happens. Might be too slow, but let's do that anyway. So we have a proper proportion. If it's too slow, then we can knock it down to 8,000 or some fraction thereof. Okay, so we are outputting the byte, we're waiting some time, and we're turning off the enable. So let's create the function that sets the read write and the register select. Just a very simple function for that, and then I'm going to say void command mode. There's 1,000 ways to do this. I could actually have something brought in here that says command mode that's defined as a specific setting, or I can have simple functions that just specify what you need to do. Kind of want to do it this way, but we can try both ways. We'll see what happens. Command mode, and let's see, void character mode. Let's see how many things we're going to be duplicating here so we can make the code more efficient later. First, let's set the read write, register select. Command mode is simply setting the register select to 0. So let's do that. Go with the register select port and then the LC register select pin, and we're going to pass a 0 to it. This is command mode. Character mode, we're sending a 1. The read write, we should already know that. To write, we send a 0. We send a low. Port and the LCD pin, bring it low so we can write to the LCD, the opposite for reading. We need to wait for about 49 nanoseconds, so I'll just put an arbitrary, each one of these will have to have that. This is where things get repetitive, but let's go ahead and see what happens. We'll use 40,000. You can already see where I'd have to change all of these if we were going to automatically scale everything down to more appropriate time delays. So maybe what I'll do is I'll set we're going to turn on the enable anyway, so we can put both the time delay and the enable in there. So let's just call that enable. Pull this time delay into that location, take all the time delays out of here, and we're going to turn on the enable. So we're going to turn the enable on in this case. Replace the time delay. So now we can enable the LCD here at the end of each one. So we're going to take the time delay out of this, put the 40,000 here. Let's do the time delay up here actually. So let's define time delay before enable, and we'll call that 40,000. There we go. So now we can just change it in the defines. We should do the same thing to the 80,000 here. So that one is between the output byte and turn off the enable. So let's say disable. So time delay before disable. There we go. Okay, let's finish up enable LCD in each one of these. Okay, so now we can, if we're going to send a character, we may not want to call this sending a character. We can, because that could be a command or a character. And we'll make a couple more, send a character and send a command. This can probably be cleaned up later on. So sending a character, we're going to have to pass in a character. So it's going to be a car. Put it into the write mode, set to write. You know, setting to write, I want to say set LCD to write, because I might have some other set to writes somewhere else. LCD command mode and LCD character mode. You know what, if I start them with LCD, that might be a better way to find things later on. So LCD set to write, LCD set to read, and every time I put in LCD, it'll give me all the commands nicely. And this can stay the same because I'm really just sending the bits to the ports and pins, so it's not really specifically for the LCD. Put LCD there. And in the main, we have to put LCD here. I might be missing some things, but we'll find out when we do the build. Okay, so we're setting it to write mode, and then we're setting LCD. Now we can look for the one we want, putting it into character mode. And now we're going to send a byte, and it will be the character. So LCD send a character will be the main sending the character to the LCD. And I want this at the bottom because I think it makes more sense for my more major, the ones that would be going into the main.c to be on the bottom, and the more basic specific only to the LCD should be at the top. So when we run this, this should actually be, the LCD should not be lit up, the read write should not be lit up, and the register select will be lit up. You know, why am I'm not going to be enabling the LCD after the read write, because it's doing that in the command or character, because I want to just write it, set the command or character, and then I'm going to delay after that. I'm wondering if the delay should be actually over here. That makes more sense. So this is where I'm enabling it. So I'm setting the read write, setting the character, enabling it with the time delay, and then I'm sending the byte, and then disabling at the same time within this. Let's put the LCD in the front. All right, I'm going to do a build just to see if I have everything correct. I'm expecting to get errors because, yeah, too few arguments. So sending a byte to the LCD data pins. We have a character here. Oh, look at that. And actually, I'm not going to be putting this one here anyway. I'm going to be doing send an LCD character. I'm going to use the A like we did before. We can remove this one. So we're just doing LCD send a character. Functions. I still don't think that I have this all right. I'm not sure if I want to do it in this way, because I could, for the read write, I could just put set read write pin and then put in read or write. But it's a little bit more difficult to understand how to do that as a person going into the main and just trying to do it for the first time. If they take a look at the LCD and everything that's in here, setting it to read, setting it to write is a lot easier to understand than setting read write and then what to put inside of it as a parameter. So let's take a look and see what outputs to the LEDs when we do this. I just noticed an area that might cause a problem. And in my previous programs, what I would do is I would do a volatile int for the I in this for loop, because if I didn't do this, then they would optimize this whole thing out. I mean, it wouldn't actually run it, because when it does the compiling of the program, it doesn't think that this is a changing variable throughout the program, then it won't actually use it and it'll be optimized out. So by making it volatile, it knows that it needs to keep that variable going in the program for the time delay. You can see that it went pretty fast, probably too fast for us to see it clearly. We can definitely see the enable LED flash on and off. So let's slow that down quite a bit and see if we can make it a little bit more discernible. And I'm going to multiply these by 2. So I'll do this 8,000 and I'll do this one, or 80,000, and I'll do this one 16,000. Yeah, it's still pretty fast. So I'm going to add another 0. I'll go back to 40,000 and I'll make it 400,000. I'll go back to 80,000 and I'll add another 0 for 800,000. Okay, that makes more sense. Okay, so the register select turns on, and then you can see that the enable turned on and the byte was sent, and then the enable turned off. So it looks like it works correctly. Just for my own purposes, I wanna show this in a loop. I'll probably pause it between the loop, or the beginning and the end, and 10 times or so. So I want to see it over and over again just to make sure it works correctly. I'll put a time delay before it, or after it actually. Why not? There has to be a time delay after it anyway, so this may not even, I mean, we have to put this in the LCD And we'll probably change this because this doesn't seem like it's LCD related, but we'll keep it in there anyway. And time delay can be 1,000,000. Let's see what that does. It would be cool to increment this every time, like A, B, C, D. Let's see. Could do that. Car letter is equal to A, and letter plus I. So this way the letter can be A and then it'll increment. It'll be B and then C, D, E, F till it exits this for loop. This while loop is here. It's just keeping the microcontroller on and not exiting out of this. Looks like it's working. We should be able to go ahead and add the LCD. I'm going to remove these two LEDs. I'm going to go ahead and put the LCD from pin 30. So we're going to need to find out where we're going to put a potentiometer. All these tie strips are going to be reserved. And also we have these two pins here that are going to be brought over as the register select and the read write. So I think the only place to put the potentiometers is over here. So let's go ahead and do that somewhere over here. Probably as close to these wires as possible so I can utilize as much of this board for other purposes later on. This side still needs to be put in. So we can see that we have the 5 volts just below the 3.3 volts. And I have the 3.3 volts right here. So we can just plug one more in and we'll have a 5 volt. Before I connect it to the breadboard, I'm going to test it with the voltmeter, just to make sure it's outputting 5 volts. Okay, I got 5.14 volts. That's good. To convert my female header into a male, I'm just going to take a header, even this out a little bit, plug it into the one end of the potentiometer. Before I connect the power 5 volts to the LCD, I'm going to connect the ground coming from 31. I'm going to connect this ground to the ground of the LCD so I know where the first pin is that we need to use, because these two are not connected and this can confuse me on where to start, because I often think that this is the VSS pin or the ground pin, but the third pin is actually the real ground pin. So I'm just going to take a jumper and put it from this position, which is the 31 on the controller card, and that's the ground pin, and it's going to go to the ground pin of the LCD. So now I'm going to take the 31 ground and I'm going to connect it to the potentiometer. So the potentiometer will have a ground and a 5 volts. So now we have the potentiometer connected to ground to the 31 pin. I'm going to go ahead and connect the wiper pin here from the potentiometer to the V0, which is all the way over here. You have the wiper pin connected to the V0 pin of the LCD. That will be now the 5 volt pin. The VDD will be the next one. And we'll connect that one to the potentiometer lead here, which is also connected to the 5 volts. Okay, now for the 5 volts. So we wired up ground, 5 volts, and the V0. So we can actually turn this on and see if we can adjust the contrast. We'll probably just get a bunch of boxes along the display. So let's see if that works. Right now we don't see anything, so let's turn the potentiometer. There we go. So the contrast is working correctly. .33 is our next pin we can connect, and that's going to be register select. So we can connect that over to the next pin here. 33 to the RS pin. Pin number 34 to the read write pin. Okay, now we need to take all of these pins, connect them to these pins. So I'm going to take these out first. The enable will be connected from 35 to the enable. Now we're going to connect the data pins. D0 will be connected to pin number 36. D1 will be connected to pin number 37. D2 is connected to pin number 38. D3 is connected to pin number 39. D4 is connected to pin number 30 to 40, actually. D5 is connected to pin number 41. D6 is connected to pin number 42. And the final one, D7, is connected to pin number 43. So we have all the data pins connected. I want to take a look at the data sheet and show you that they're emphasizing that you should make sure that the LCD or the chip that is on the LCD is not in the busy state when we're trying to send data to it. It's also saying if we don't check for the instruction, if we don't check for the busy state, then the time between the first instruction and the next instruction will take much longer than the instruction time itself. So it looks like it's just a function of taking a longer time, but in our initial tests of the LCD, we're not going to be checking the busy state, and we're going to be increasing the time quite a bit anyway, so I'm just not going to worry about it right now. And following that, they have a list of instructions that you can use with the LCD. On table 13, it shows some of the steps you have to take to write characters on the LCD. And this is table 13, and it shows a 2-line display, which is what we're using. And you have to go through a certain order of operations here. You have to initialize, which is just turning it on. And this will set the LCD to 8-bit operation and selects 2-line display and 5x8 dot character font. And then we turn on the display and the cursor. You can see the cursor there. And this command is telling the cursor to increment to the right one every time we send a character. Sometimes I don't actually like to put the cursor on here because when you're putting out information really, really fast, that cursor will be flashing all over the place. So you might want to turn that off in your application. And we may do that in this tutorial as well. And this is writing data to the LCD. And they're calling it the CG RAM or DD RAM. That's just the memory within the LCD, and it's just writing that to the display, whatever is in that part of the memory. So it's actually this part right here. So if we look up 010010072, let's see what it is. Yep, that's an H. So you can see that these bits create an H in binary. And you continue doing that and keep writing data to the LCD. So let's go ahead and start putting in some of this information in the program. We don't need any of this stuff anymore. First, we need to make sure that it's going to be in write mode. Let's first create a function to write a command. We'll just do a copy and paste of the character and send a command. Well, they called it instruction in the data sheet. But I've been using command for so long. Yeah, I'm only using it in 2 places. Send in an instruction. And I'll change the LCD instruction mode. Yeah, that's all I'm using, I think. So we want to make sure that it is set to write. The LCD is in instruction mode. Let's save first. Gotta write the whole thing again. Okay, so we set it to write, set it for instruction mode, we enable, and then we send the byte to the LCD data pins. So the first one is, actually, I don't think we want to do that. We want to make sure the instruction mode, the RS is low. Okay, so in the main, I'm going to go ahead and keep this as an A, because eventually we're going to be sending a character anyway. LCD send an instruction, and the instruction is going to be in binary form. I'm going to use 8 zeros, and I'm going to put the ones where they need to be. In the data sheet, where you see these stars, just means that it doesn't matter what you have in here. It sort of ignores those. So we have 2 zeros, 3 ones, and 3 zeros. And this one is set to 8-bit mode and 2-line display. So let's create another instruction. And the ones in this one are located right next to the last one. And this one is turning on the display and cursor. Sending another instruction, we need to set the mode to increment the address by 1. And now we can start putting in the letters. Let's try newbie hack. It put ABC in there first, which is kind of weird. I have no idea why that happened, but we'll find out. You'll see how slow it's going on. So let's reduce the time delay and see. At this particular point, I don't know what's going on, but I'm going to try this instruction to make it go to the second line, just to see if it goes to the second line or it creates some character that would be associated with this binary number. So I'll put the hack on another line. Go to the next line. 1, 1. Okay, so let's see what happens with this. Reduce these 400. And 800. It should be instantaneous. Okay, it did go to the next line, which is kind of interesting, but it shows an A. It didn't clear the screen. Let's see what is the command to clear the screen. Generally, when it turns on the display and it resets, it should do all that. Clear display. There's just a 1 on the end, so let's do that. Let's clear the display. All right. There we go. Reduce the time delay just to see what happens. Okay, so that's too fast. Increase the time delays and okay, newbie hack. All right. Instead of sending characters individually, I would like to send them as a string. Pointers are just pointing to a specific memory location, which are called addresses in programming terms. So in the microcontroller, you're going to have a specified location for memory. Memory is actually the main component in microcontrollers and computers, and there's addresses for almost everything and to control everything, even registers and things like that. And the memory is like little boxes. You can think of it as like a grid. So let's say this is just a portion of that memory, and we specify a character pointer, which is specified like this, and we store a set of characters within that car data type. It really is only specifying the location of the first character because the car data type is only one character. It can't hold all of this. But by putting the pointer there, it is specifying where the first one is located. So let's say that in our memory, the location is here. And by using the pointer feature of the C programming language, it specifies this location, but it also not just specifies the location, it knows what's inside of that location. And this data type, of course, is going to have some kind of name. Let's say we call it text. Well, text is the actual variable that we use to access this location. And if you increment text equals text plus 1, then it will know what's inside of this location. So this is plus 1, and this is plus 2, and so on. The cool thing about specifying pointers over arrays is that you don't have to declare a specified number of locations, because at the very end, it will add a null character here. So we can have a loop that iterates through all of these locations, and then at the end, all we do is we either test for null or we see if the character within that location is greater than 0. I know that way works because I've already done it. I haven't really done a iteration that tests for null in this particular type of context. So let's go back to the program and add another function into our LCD functions. So we're going to go to the LCD functions and let's go to the end here where we actually send a character and send an instruction. This function doesn't need to return anything, so it's going to be a void, and we'll call it LCD send a string. So what we're going to pass in is a car data type and a pointer, and this is where we name the variable that we're going to be using within this function. And here we can say string of characters. Within this function, we're going to be sending a character multiple times until it gets to the end of that string. So we're going to go ahead and use the LCD send a character, and then it's going to be waiting for a particular character. So we're going to be using the string of characters. We're going to use the pointer because it needs to know where it's located and what is inside of it. String of characters. Okay, so that's actually looking at the very first character. So if I actually ran it right now, it'll only, if we're using the word newbie hack, it will only show the first character, n, and then the function will be completed. Let's see what it would look like if we did this in longhand. So if you wanted to show this without a loop, then we can do this. You might find it strange that I'm putting the plus plus on the left-hand side of this variable, and that's because this is actually the first character, and if I put a plus plus on the left-hand side of it, it would increment first, so it would be actually looking at the second character. If I put the plus plus on the right-hand side, then it would look at the first character and then add 1 to itself after it has passed in the first character. If I do it this way, then I'm going to have to do that way all of it. So we just need a way to do this multiple times and stop when it finds that null character. If we want to try using the null as the condition, let's go ahead and see what that would be. So let's use the while. We'll take this line and put it inside the while loop. And this is exactly the way it needs to look inside the loop. It still needs to be in this form with the plus plus at the end. So the first time it goes through the loop, the first instance of this, it'll only be considering the pointer and string of characters and not the plus plus. So it'll look at the very first character. So what do we put inside here? Well, why don't we just put this inside there? Because what I've learned is that a condition is true if it is either non-zero or non-null or not null in the ANSI C language. So if this is not 0 and it doesn't contain a null character, it should be able to be true and go into the loop. So let's actually see if this works. Let's go ahead and put this into the main.c. What I want to do is I want to do the character by character on the first line and then the string on the second line. So I'm going to put this above the, I believe this actually clears the display. So I'm not sure if we actually need this because we're turning on the displaying cursor here and it may actually do the clearing as well, but let's keep this in here. All right, so I'm going to introduce the new function. I didn't save the file yet. Send a string, and then we're going to send the string newbie hack in lowercase so we can actually see the difference. It worked. And it looks like the condition that searches for a null or only accepts either a valid character actually works. So that's awesome. Okay, let's see how we can send numbers to the LCD. This is our skeleton code, and we have the LCD initialize and the LCD setup display. When we were looking to send a number to the LCD, we can't just send a number by itself, like LCD send a string, and then type in the number 200. This is an actual number, and this function doesn't accept numbers. It only accepts strings. And another way we would want to do this is to have a variable, let's say an integer, and it's equal to 200. We would want to be able to send a variable to the LCD as well, but obviously we know that we can't do this because this is not the correct data type in this function for send a string. So let's see how we can do this. First, we need to take this integer and we need to convert it into a string. So the LCD send a string will be able to handle this. So the way we do that is using another function called sprintf, but we don't have that available to us right now because we don't have the proper include for that library. And the include is stdio, which is the standard IO library for the C programming language. So we're going to include stdio.h. So we're going to use the function called sprint. You'll notice that there are some inputs that it's requiring. And the first one is a car. So let's go ahead and set up a car variable. And let's say this is string number. We'll just call it string number. And then we'll leave it at that. So we should have the variables set up for us. So we're going to start off with putting the string number here as the first input. The second input will be a format. So this is going to be in the form of a string. And the first character we're going to put in there is the %. And then the following character will be a letter determining what format the next variable will be. And in this case, it's going to be D for integer. I believe you can also use the letter I, but we'll use D because that's commonly used. And then the next input will be the actual integer. So let's just do a copy and paste of that. And you'll see that there doesn't seem to be any errors. So let's go ahead and let's go ahead and put this one in the send a string, because this is the actual string that will contain the converted number. So if I create that as a pointer, let's initialize it with an empty string. Sometimes it's actually good to have an array initialized because in the LCD, you don't want the number of characters to exceed a certain amount because you only have so many characters available on that LCD. So sometimes it's good, but I'm going to try it like this. And we know that like an integer, if we know what the maximum minimum values are going to be, then it shouldn't matter. Okay, so let's go ahead and flash the microcontroller and see if it works. And it looks like it did not work. Just to make sure that we're able to actually do something on this. Okay, we can't even output a 200. It looks like I am unable to use the pointer type or the pointer to a variable. It just doesn't work. And I'm wondering if it has something to do with memory issues. So we have to make this an array. I'm going to use 5 characters. This is only 3 characters, but it doesn't really matter in this particular case. That's just in case I have a number that goes up to 20,000, an unsigned number. I can actually put that on here. That's only for numbers above 0, unsigned. Unsigned means it's not going to be negative. Let's flash the microcontroller. Let's see if we can create another function that only outputs numbers. So in the LCD functions, we're going to essentially place this in the function. So I'm going to copy this, and we'll create another function that outputs numbers. So this is going to be something that doesn't require return, and we'll call it LCD send an integer. I guess we could make it so it sends other variables like doubles and floating points, but I'm going to make this simple at first. So we're just going to make it so it sends an integer, and we're going to want to receive the actual integer. So we'll make it a signed integer just in case it has to be a negative, and we'll call it integer to be displayed. And that should be all I need to pass in. All right, so let's go ahead and paste what we had. So the string number can be just, I would like to make this a little bit more. You know what? There's another number we need to pass in, and that is length. This is going to be an unsigned integer. Actually, it can be a, let's see, length of, do I have this variable type available to me? Oh, we'll find out. We'll call length of digits. That should be easy enough to understand. We'll use that here. And then the integer will be equal to this, but we don't really need to actually use that line. We're going to copy and paste the actual integer to be displayed in the sprintf function. And that should be it. So it should just go ahead and send that string. So let's try this out. I'm going to do a copy and paste of this. Oh, why not just do it the right way? Save all this. LCD, send an integer. There we go. I don't like that big N. Okay, so integer to be displayed. Let's just call it 150. And then I'll need 3 digits for this particular number. I didn't put the include in the function, so I'm going to do that here. I got an error that said that it didn't know what the sprint command was, or the function was. So I need to actually include that in here, because you'll notice that I did this include after the LCD functions. And since this LCD functions uses this command, or this function, I really do want to put it in this header file. Okay, we got the number 150. That's good. You might be wondering, well, why do I have to put a specific number here? This actually should be a max number. I'm going to change the input variable to say max length of digits. And generally, when you're making something for the LCD, you have, let's say, 16 characters on the first line. And let's say you wanted to show a particular number, let's say pressure. And now you know that you have 6 characters remaining on that line. So you can just go ahead and put in 6 because you're going to use the rest of that line. Or you can not have a space here and you can have 7. And now you'll know how many characters or digits you can have on that line. And you want to also make sure that this number is not going to exceed that number of digits. So we have created a new function that outputs integers on the LCD. You can easily just go into the LCD functions and create this for any type of number, let's say floating point. All you would have to do is replace floating point. Yeah. LCD send a floating point number, and this is going to have to change to float, and this can stay the same. Remember that the max digits needs to consider the actual decimal point and the negative sign if one is going to be there. And the next thing we'd want to change, obviously, is the floating point number to be displayed, and we would replace that one. And the reason why I'm changing this variable, we really don't need to, but when we're actually using the function in the main file, or in the main code, it'll tell us what this is, what it's asking you for. So we want to make sure that we have that correct. And then this format has to change from D to F, floating point. You can also use the %E for the shortest representation of the floating point number. I'm not sure what that really means because I haven't really delved into that yet, but you can go look at the specifier for the printf under the ANSI specifications, and you can see all of the output types for, say, integer, octal, hexadecimal, floating point, scientific notation, even pointer addresses can be shown. So you have the possibility of creating as many types of numbers or representations that you want. And it doesn't have to be just these 2 characters. You can actually create going to the next line and all kinds of other types of formats that you want if you feel that it's necessary to put that in there. Okay, so let's go ahead and use this one and see if it works. I'm going to change this to F, save the files, and maybe I'll go to the next line. So which one is that? Let's see, send an instruction. Go to next line. Okay. And then we'll send a floating point. Okay, and the number can be, let's say, 256.67. And then the max number of digits would be 1, 2, 3, 4, 5, 6. Let's say 10. We have 16 to work with, but actually, let's go ahead and put in something before that. So there's 6. Let's make this 7, just in case there's more digits we need later on. And LCD send a string, and we'll call this float. Let's see if this works. Build. Okay, length of digits undeclared. That's 183. Let's see what we did wrong there. Oh, max length of digits. Yeah. We have to do the same thing here. We changed that. All right, let's save the files and do another. And it looks like we have no errors. Let's go ahead and flash the microcontroller. Okay, we have 150, and you can see that the float, it actually gave us a few more numbers on there. So it's odd that it did a conversion and then added some more digits, 0.670013, and that's 10 digits. And I only asked it to print out 7, so I wonder what's going on there. After a bit of research, I found that the function snprintf is actually a better function to use because it allows you to restrict this number of digits that it stores in this particular array using another input parameter. And I'm just using the max length of digits that I'm passing in anyway, which is going to be the size of the array. And after a little bit of testing, and you'll see on the next portion of the video, that adding the +1 will provide the correct number of digits for what you specify in this input parameter. I haven't used it in the integer function. I'm only using it in the float function. Since the integer was working in the previous attempts, I'm going to keep it this way until I see a problem where it is outputting something that I wouldn't expect. A really good indication of how well this idea works would be to actually show the numbers changing on the LCD. So let's try to do that. I'm going to create a for loop that counts up from 0 to, let's just go to 10,000. So we want to put the function inside of this loop. We don't need the go to next line, and we'll take these out. So we'll just replace the 150 with I, and 10,000 would be 5 of them, but that doesn't really matter. 7 is fine. And we need a time delay in here, don't we? Let's do 10,000. Let's flash the microcontroller and see what happens. Oh, it's not clearing the display or going back to a specific place on the LCD. And that actually brings up a good point that we don't actually have a command that specifies the location where the cursor should go. So let's do that. I guess for this small task, just to see what happens, we can put clear the display on here, but it could make it so it looks more like a ghosted image. So let's see what happens. Okay, that looks like it works. The reason why you can see the numbers so clearly is because it first clears the screen and it sets up the display, and then it shows the integer on the screen, does a time delay, and the time delay gives it some time to show on the screen, on the display, and then it does a clear again. The only function that we're really missing to add to the LCD functions is to insert characters at any location on the LCD. Let's say we want to have a number to be placed in these 3 digits, and we always want those digits to be in these 3 locations. So you'll need to know what location that particular digit is. The alternative would be to always clear the display and start from this location and then start writing whatever we need on this line, and then going to this line and writing whatever we need to go on this line. And in the case of just putting a number in this location, we would have to first clear the display, go to the next line, and then have this many spaces to this point, and then write the number. But fortunately, there's a nice little command that you can locate the cursor in any of these boxes or digits. And it's called the DRAM address. Each one of these is a DRAM address. And to be able to access this instruction to position the cursor at any one of these DRAM addresses, it is 0x80 in hex, and that's the beginning. So you have actually, this is the binary number you have to maintain. It's a 1 at this location. And this, by the way, this is at D0 through 7. So this is the data pins, and you are just sending a byte. This would be considered the byte, as we all would know. So the instruction would always be 80, and then these remaining 7 digits, we know that 8 digits, or an 8 binary number, would be 256 as the maximum value, but 7 digits would be 128 as the maximum value. But you know that there are not 128 display positions, but we're talking about accessing a controller for standard displays, which may be displays of many different types of, let's say, multiple lines and multiple positions per line. So you could have almost any configuration as long as there is not a maximum of 128 positions for an LCD display. So this initial number would correspond to this address. But we don't actually know
what number would correspond to this address. So let's find out. We can do this by making a little program that loops through each of these digits. I want it to iterate through the entire display, but if I miss something, then it'll start all over again. So I'm just going to make a simple loop as long as I is less than 128 and I is incrementing. So let's first position the cursor. So we're going to send an instruction, and this one is going to be 0x80. 0 be 1, that's the equivalent of 0x80. And then we're going to send a character, send a string. We want to send an x. Actually, I think I want to send a space and then an x. So what this does is it erases the x before it. So it looks like it's a walking x. If I'm going to do this, I'm going to think that the x is actually one step ahead of it. So I'm going to start out with -1 here. I'm wondering if that's going to cause a problem with my sending instruction. Okay, now I want to actually show the number of that position, the variable I is, so I know where that location is. So I'm going to position it at the same location. That's here, which is just the beginning, the first position on the LCD. And then I'm going to actually print out the I. I'm going to send an integer. I'm going to display I, and it's going to be 3 characters max. You know, I don't have to do this -1 here, do I? I can actually show it here as a +1. And it's going to start on the second one, but I'm not really worried about it, because this would be the I. This position here would be I, and this position here would be I +1. So we want to show I +1 at the first position, what the actual number is. And now I want to add a time delay. And I'm putting the time delay at the end because I want to first show it, and I want it to be on the screen for a little while so I can read it and it won't disappear. I'll put it there for 100,000. That should be good enough. Might be too slow, but we'll find out. Okay, let's see if this builds. There are no errors, so let's go ahead and flash the microcontroller. Okay, I flashed the microcontroller, and it doesn't seem to be doing what I expected it to do, so let's see what happened. Oh, I see my problem. I didn't add the I to this. Let's try it again. And I needed to, because this is going to be adding I to this number, we'll just add it to here. Since this is already a 1 in this position, we're just adding a number to it. This is just a number. So by adding the I to it, it's just incrementing this number. So let's flash the microcontroller again. Okay, that seemed to work. It looks like it's a little bit too fast, so let's slow that down a little bit. I'll make it 500,000. Okay, that looks better. So we know the top line is from 0 to 15, so that makes sense. It would be like indexed from 0, so it would be 1 to 16, so 16 positions. You can see that it's still counting up, but it hasn't gotten to the next line yet. Now 40 was the next line, so 40 through 55. So let's take a look at what we need to do to create our function. So we know this is 0, and the next line was 40 and 55. So I want to make a function that, let's say, LCD set cursor position. And I want my inputs to be X and Y. But how do we make an X and Y coordinate if we have these numbers? So say I wanted to have the position be here at 46. Well, my X value I want to be 6. And my Y value I want to be, do I want to have the index from 1 or 0? So if I'm going to make this one 6, this one has to be 1. I think I'm going to make it indexed by 0. So this would have to be Y equals 1. So if I have X equals 6 and Y equals 1, then the formula would be position is equal to X plus Y times 40. Let's plug in the numbers. So if X is equal to 6, X 6 plus 1 times 40 would equal 6 plus 40, which is 46. If it was at the 6th position on the first line, it would be 6 plus 0 times 40, which would equal 6 plus 0, because anything times 0 is 0, and that would equal 6. So that all makes sense. So let's go back to the program and see what we need to do. So let's do another for loop, but I'm going to do a nested for loop where I have a Y, or X actually, X, and this will go up to 15, and then I nest it with a Y loop. Y is less than or equal to 1, and Y plus plus. So now I can cycle through the entire display using a nested loop, and it'll only show on the points that I need it to show. So let's send the instruction. I'm going to do this with the hexadecimal code, and I'm going to add x plus y times 40. I'm going to contain the y times 40. Okay, so let's put a string. I'm just going to put an x in this one, and then I'm going to have a time delay. I'll make that 500,000 again. And this time, instead of putting that space behind the x, I'm going to erase the x on the next one. So I'm going to use the same position and delete the x just with a space. And since there's no time delay afterwards, it will erase this x immediately and then put the next x on the next location. So it should look seamless. Okay, the microcontroller is programmed, and it looks like I got the nested loop backwards. So that makes sense. It's going up and down the y and then the x. So I'm going to reverse these. Okay, let's try it again. Okay, looks like it's doing the right thing. It's going along the x on the first line, and right when it gets to the end, it should go straight to the next line. And it looks like it didn't go to the last position, and I probably have it because of the less than. Yeah, it should be less than or equal to here. So let's do that again. Let's test that one. 0, 1, 2, 3, 4. Will it get to 15? Yes. Okay, so it looks like the formula is correct. So let's go ahead and make a function. So I think the function is going to be, what did I say last time? LCD set cursor location. And then I'm going to bring in an x. I can make this a u, 98t, x, and y. Okay. Well, it's going to be a void. We're not returning anything. And the first thing we need to do is send an instruction. And this will be 0x80 plus the x plus y times 40. And this is for this particular LCD. So you'll need to plug in the correct number here for what position the next line starts. You could make a define macro that has this number in it. Let's go ahead and try that, see if it works. I didn't save it yet, so it's not coming up. So I'll just put x and y here. Actually, these are ints. I wonder if I can put u int. I don't think I've tried this yet. See if that works. So I'm going to do the same thing on this next line. So if this works, we are successful in making that function. Still works. So now you know how to set a particular cursor location on any part of the display. Let's talk about analog to digital conversion, or ADC. Analog to digital conversion is where the microcontroller will take an analog signal or an analog voltage, specifically in the form of a waveform over time. So this would be time, and this would be voltage, let's say 0 to 3.3. And you have a device that outputs some kind of voltage over time. So you can take the output of this device that is showing a voltage. Over here it's 0 volts, and over here it's 3.3 volts. You can take that voltage and you convert that to a number that you can use in computation. And you have to think of it in a way that something that you want to sense, like something in the environment, will most likely give you an output in a voltage, and in a voltage between two specific reference voltages from 0 to, let's say, 3.3 volts. So let's say this is 60 degrees here, and this is 70 degrees. This would be the voltage at 60 degrees here, and this would be the voltage at 70 degrees. It means that the voltage here, this would be around 2 volts, and this would be around 2.3 volts. Microcontroller is not going to take a voltage and then give you 60 degrees unless you create a computation for that. It's going to give you an output of 0 to, if it's an 8-bit number, 255. And if it's a 10-bit number, this would be 0 to 1024. In the 8-bit case, this 60 degrees would be around 153, and the 70 degrees would be around 179. So you could take this number, or these numbers, and use them in some kind of computation that would yield the actual temperature, or whatever you would need to do with that particular number at that temperature. You don't really need to convert it to a temperature if you're really going to use it in some other kind of computation. So you can have the microcontroller constantly reading what this temperature value is, or whatever this device is reading from the environment. And this will happen through time. So when you turn your microcontroller on, you can start reading the signals here from the analog device. And it'll start out at 0, and then these would be like 8-bit numbers here. and then you'd have another one here. That would be around, let's say, 102 in 8-bit number. I'm basing this on about 40% or 40% of the 3.3 volts, which is about 1.32. So I'm just taking 3.3 and multiplying it by 0.4, or you can also take the 255 and multiply that by 0.4, which is 102. And then you can get the next conversion here, and that would be somewhere in between 153 and 179, let's say 165. And then here, so it'll keep doing these conversions. And I'm showing it to you in this way because a conversion happens between two periods of a time frame. And this is important because the ADC, the analog to digital converter, needs to be connected to a clock source in your microcontroller. And that clock source has to be pre-scaled or scaled in a way that it allows time for a conversion to happen. There could be a whole bunch of clock cycles between this, but it needs those clock cycles to do one conversion. I believe that number is 17 microseconds, which is what I'm going to start doing in the beginning programs. Is I'm going to use about 17 microseconds, which is actually a long period of time and is one of the periods of times you can use in the analog to digital converter. So what can you use analog to digital conversion for? Some of the applications I can think of are sensing, which are generally environmental sensing or sensing things from the environment. And that could be temperature. It could be tilt from an accelerometer. It could be angular velocity or the speed at which something is tilting. And that would be from like a gyroscope. This temperature would be obviously from something like a thermistor or a thermocouple. It could be used for sensing distances, either through laser or sonar, radar, or infrared. You could even use it for controlling, like with a potentiometer. When you turn the knob of a potentiometer, the voltage goes up or down, and you can take that number and you can apply it in various different ways. Maybe controlling a menu system or controlling the volume of some audio output. You could also use it for recording audio, which is probably in the sensing application or sensing category, because that would be a microphone. You can convert these analog variations to a set of numbers for each point. Each of these points could be a number that is stored as a digital recording of audio. The list of these applications go on and on. There really is an endless list of how you can apply analog to digital conversion. With the microcontroller that we're using, there are 16 channels of analog to digital converter pins that are located along the microcontroller. And there's also one channel within the microcontroller that actually has a temperature sensor. And then there's another channel for voltage reference. And this is a voltage reference that is absolutely accurate. It is a band gap voltage reference, which means that it's a constant voltage reference no matter how much variability you're having in your supply, in your power supply to supply the microcontroller. And this is important because the voltage reference must be very accurate to be able to give you a good reading constantly on a analog to digital conversion. You might notice that I use the word channels. Channels is the way you would specify the analog to digital controller's separation from one analog device to another. Pin 15, for instance, is the ADC in 1, which is considered channel 1. And pin number 16 is ADC in 2. And being that these are channels and not just regular input pins, you cannot have a conversion on the number 1 at the same time you're doing a conversion on number 2. This has to happen one after another. And let's say we have an analog signal coming into 2 and into 1, and you want to read both of those and use both of those numbers in some kind of computation. There is a thing called scan direction, and it will do either this one first and then this one second, depending on how you program and how you set up your channel register. Number 17 is ADC in 3. Number 20 is ADC in 4. Number 21 is ADC in 5. Number 22 is ADC in 6. Number 23 is ADC in 7. Number 26 is ADC in 8. Number 27 is ADC in 9. All the way to number 8 is ADC in 10. And these are the alternate functions, by the way, of these pins. These pins are used for general purpose input-output, but they can also be used for the analog to digital converter. And pin number 9 is ADC 11, and pin number 10 is ADC in 12, and pin number 11 is ADC in 13, and pin number 24 all the way back over here is ADC input number 14. And number 25 is ADC in number 15. It looks like we only have 15 inputs or 15 channels. And the ADC number 16, I'm just going to write it over here somewhere, is the internal temperature sensor. And the ADC number 17 is the VREF. Now you know how the microcontroller is set up and what input pins you can use for inputting voltages between certain voltage minimums and maximums, or what steps do you need to take in programming analog to digital conversion. There are certain steps you have to take to actually set up the analog to digital converter to start doing the conversions, and then the actual conversions themselves. So let's see what those steps are. The first one is called calibration. And what this does is each microcontroller that is put out in the factory is calibrated to in a certain way. It has a specific setup that when the calibration is done in the analog to digital conversion setup, it calibrates according to what is set up in the factory for that particular chip. So when you do the calibration, it calibrates the voltage reference and the converter so that it's going to have a repeatable reading every time, meaning that a particular temperature will give you a specific number and it'll always be that number every single time. And then you have connecting the ADC with a clock. And the clock source for the ADC is the HSI 14. And we'll get more into this later on as we program it. The next step is to enable the ADC. And then the last step, you establish the conversion, where you set up the channels, specify the scan direction, establish the start of the conversion, and then you can grab the data. And the conversion can be in an 8-bit number, a 10-bit number, or a 12-bit number. The resolution, which is the 8, 10, or 12 bits, can be dependent on the actual application, whether the sensor or whatever you're controlling requires that amount of resolution, or if it even can give you that amount of resolution, where the analog doesn't really need that much resolution because maybe it's controlling sprinklers or something like that, or if it requires a lot of resolution where it may be connected to some kind of safety application or a mission critical application. Now you should know a little bit about analog to digital conversion. In the next video, we'll take a look at how to set up the circuit, which is extremely easy, and we'll start getting into the programming.